Anis, could you check a YouTube live? I just started.
Well, I checked and it seems to be working.
Oh, okay. Oh, hi, Mark. Good morning.
Well, I checked and it seems to be working.
Oh, okay.
Oh, hang on. Good morning.
Ah, no, somewhere.
Should we start?
Yeah, just give me 5 seconds. Yeah, let me start recording. Okay, recording is complete. Okay, I'm ready.
All right. So, hi everyone. Welcome to the first session of day 2. We have 3 speakers in this session. So the first speaker is Mark Inmers. Mark, you have 1 hour, so maybe I'll give you a reminder when you have, say, 10 minutes left.
All right, thanks very much.
Over to you.
Good, yeah, well, thanks very much for inviting me along to this, this online conference. It's good that we still have online conferences, even though we suffered from them in the Corona time. But it's the way of the future, I think. So today is about one way that beyond the standard model physics can be observed, and that's through gravitational waves from phase transitions in the early universe. And just a few very basic comments to make in that we know that at very high temperatures and pressures, the state of the universe, the matter in the universe was different. Before 1 millisecond, quarks and gluons were free of the bounds of being confined to hadrons, and before 10 picoseconds, elementary particles were, ignoring thermal effects, massless. And that may not be the end of physics in nature, and so there may actually be new symmetries and interactions whose state changed in the even earlier in the history of the universe. And such changes of state can lead to departures from equilibrium and homogeneity, and therefore the generation of shear stress in various ways. If there's a first order transition, that was first, I guess, pointed out in detail by Steinhardt 40 years ago. You can also get topological defects, as we heard yesterday. And this doesn't depend on the order of the transition, just the symmetries that are being broken. And one of the reasons for thinking about phase transitions, and in particular first order phase transitions, is that the departure from equilibrium can give rise to one of the conditions required for generation of the baryon asymmetry of the universe. This has also been part of the furniture for early universe cosmology for quite some time. But the main thing about first order phase transitions that I want to focus on is that they can produce gravitational waves. This was also pointed out by none other than Ed Witten in the 80s. So when we start thinking about the standard model, we sort of draw a fairly gloomy conclusion. I'm not mentioning QCD. That's a crossover. The electroweak transition, at least in the standard model, is also not a first order phase transition, as was pointed out by some groundbreaking work in the 90s using new non-perturbative techniques of dimensional reduction combined with 3D lattice studies. So the standard model doesn't have a first order transition. It doesn't boil or bubble or condense. It just behaves like a supercritical fluid as you cool through 100 GeV. So that does mean that if the standard model is all that there is, then we don't expect gravitational waves from the early universe. But most are pretty sure that there is more physics that we need to explain, for example, baryon asymmetry and dark matter. So then the search for gravitational waves from a first order transition becomes a search for physics beyond the standard model. Just a little aside that actually the standard model transition, I put a picture of boiling water on the previous slide. The standard model transition is in the same universality class as the liquid vapor transition in ordinary water. So the boiling water was not so gratuitous after all. So with this, let's explore now the consequences of what a first order transition in the early universe would look like. Bearing in mind that we're not talking about water now, we're talking about an ultra-relativistic plasma. But nonetheless, the transition is thought to proceed by the nucleation of bubbles, or condensation of bubbles of the low temperature phase. And they grow, they generate pressure waves in the hot fluid, and these hot rings are sliced through a numerical simulation and showing the blue color is stationary fluid and the hot rings are moving fluid. So this kinetic energy or pressure waves in the fluid generates shear stresses and gravitational waves. And one of the exciting things in the past few years is to understand that the gravitational wave spectrum has a lot of information about the state of the fluid and the phase transition. So what frequencies can we expect for those gravitational waves, and how might we see them? Well, by thinking about the time at which the electroweak transition happened, and realizing that no gravitational waves with a longer period could have been generated, you can redshift those periods to today and realize that an electroweak transition has a lower bound on the gravitational electroweak scale transition has a lower bound on the gravitational wave frequency of about 20 microhertz. And we'll see in detail what in a little bit later what exactly controls the frequency of the gravitational waves. But anything at a higher frequency can be expected. That puts us squarely in the sensitivity range of planned space-based interferometers, which are optimized at around a millihertz. So, of course, probably all heard of one of these planned missions, LISA, the Laser Interferometer Space Antenna, due for launch in the middle of the next decade. That launch date changes a little bit from year to year. At the moment, I think it's 2035. And the idea is that it will be able to observe for 4 years, and maybe even if things go well, it'll carry enough fuel to do it for up to 10 years. And what is it? Well, it's 3 satellites orbiting the Sun, a little bit behind the Earth, measuring their relative velocities with by exchanging laser beams. That's what these lines along the triangles are. And it'll be extremely sensitive, and it will be able to measure characteristic strains of 10 to the minus 21 at frequencies between 1 and 10 millihertz. So that's in terms of characteristic strain, the relative change of the distance between them. That's about the same as the as LIGO. What will it look for? Well, don't build a satellite just to go and look for the TeV scale A universe. What it's going to see a lot of is white dwarfs in our own galaxy. There's a good chance that it'll see some black holes on their way to becoming LIGO signals. A very good chance, and this is basically what it was built for, to see merging supermassive black holes in the centers of galaxies. And they will be very loud signals moving through the detection frequencies, and finally merging and ringing down. So what would a TeV scale, would a TeV scale phase transition look like? Well, it would hopefully show up as a sort of a peaked spectrum somewhere, somewhere in this range. There are other missions in various stages of planning. Daigo, a Japanese mission, and Taiji and Tianqin are Chinese missions. Taiji is essentially very much like LISA, same size and scope. Tianqin is an Earth orbit mission, which is targeting higher frequencies. So let's get back to phase transition and just try and give names to what we saw in the movie. So first of all, the phase transition needs to nucleate, so some bubbles need to nucleate. There's a thermal barrier to that nucleation, but it's decreasing as the temperature goes down, because the energy barrier decreases with temperature typically in these thermal transitions. So bubble nucleation happens all in a rush, because the nucleation rate grows exponentially, and bubbles then expand because the pressure difference favors expanding bubbles when you're below the critical temperature. They collide and leave behind this mess of pressure waves or sound waves, which oscillate for some time. And what is the time? Well, the time is set by the nonlinearity time of or the shock appearance time of the fluid. Actually, this is a general nonlinearity time for hydrodynamics. It's the length scale of the flow divided by the RMS velocity, and the length scale is determined by the bubble density, by the mean, average number of bubbles per unit volume. And the RMS fluid velocity is determined by the energy released in the transition. More about that later. The time taken for once the bubbles start nucleating to once you're entirely in the stable phase is actually this coefficient beta, which is the logarithmic, the time derivative of the logarithm of the nucleation rate per unit volume. All right, a slide with lots of equations, but it's to say what is the theory that describes this process. Well, one can reduce it to a scalar order parameter and an ideal relativistic fluid. And let's assume that the transition is sufficiently rapid that we can neglect the expansion of the universe while it's happening. That's not always the case, but that's the first port of call. So the energy momentum tensor of the system consists of a scalar field and an ideal relativistic fluid. The scalar field has its Higgs field, if we're talking about an electrolytic transition, has an equation of motion, which is partly controlled by its effective potential, which should look like this in a first order transition, so a metastable phase and a stable phase separated by an energy barrier. And it's also in general coupled to the fluid through modeling some frictional interaction. So gradients in the scalar field put the fluid out of equilibrium and generate some entropy. These are the equations for a relativistic fluid with a scalar order coupled to a scalar order parameter. They are partial differential equations, look like a bit of a mess written this way, but they are basically partial differential equations for the energy density and the momentum density of the fluid, and they receive they are sourced by the fluid, by the scalar fluid. So one can study the system numerically. One discretizes it. There are various schemes. The one we use is one due to Wilson and Matthews, but there are many other approaches. But the thing that you want to measure is the metric perturbation that's generated, and you look at the shear stresses, which are hidden in here. Use them to source the metric perturbation. And there's a little trick to project out the gravitational, the transverse traceless parts in the end. The other bits don't matter in this in the symmetric 3x3 tensor. All right, so what's the so we're going to look in two ways. First of all, I'm going to spend the next few minutes talking about how this effective theory is connected to fundamental theory, and then I'll go on to talking about the hydrodynamics, gravitational wave production, and briefly look at prospects for their detection. So as I mentioned, the connection to the fundamental theory is mainly through the scalar field. The scalar field has two places where the underlying theory appears, one of which is the effective potential, and that's an equilibrium or I guess strictly quasi-equilibrium quantity, because of course if you're in a metastable state, you're not quite in equilibrium. And it controls some parameters, which are the nucleation temperature, alpha. What is alpha? Alpha is, well, broadly speaking, it's the latent heat, the energy released by the transition relative to the total thermal energy of the system. Beta, we've already mentioned that, that's the transition rate, or the inverse lifetime of the transition. Also the sound speed, or sound speeds, because there are two different phases, and the effective number of degrees of freedom is in there as well, and that controls the Hubble rate at the nucleation temperature. The other connection to fundamental theory is the effective coupling between the scalar and the fluid, which to lowest order in a gradient expansion and kind of looks like this. By the way, I forgot to say an annoying feature of fluid dynamics is that they use W for the Lorentz gamma. It was written on the last slide, and I forgot to highlight it. And this, in combination with the other parameters, determines the speed with which the bubble wall expands and controls the friction and therefore the terminal velocity. So there are other things that you might want to know, which are sort of convenient, because what you really want to know is what the gravitational wave power spectrum is, which you could parameterize perhaps by some parameters, a peak amplitude, a peak frequency, and some other parameters which you could call shape parameters. Between the thermodynamics and the gravitational waves, there are some intermediate quantities that are very convenient to use. Of course, the Hubble rate is one of them. The kinetic energy fraction, so that's the fractional energy that ends up in kinetic energy in the fluid, and also the mean bubble separation. As I mentioned before, this controls the overall length scale. And to a first approximation, it's a function of the transition rate and the wall speed, but actually it picks up some to a second. If you, in certain circumstances, it also depends on the heat released by the transition. Okay, so these are the parameters for the phase transition, which ultimately come from some underlying theory, and we're trying to observe them by fixing these parameters by gravitational wave observation. All right. So let's say a bit more about some few remarks about the microphysics. Actually, phase transitions have been around for actually 50 years now. It was first pointed out by Kirchnitz and Linde that a weakly coupled gauge theory could have a first order phase transition. And that's essentially because if you look at the free energy density of a plasma with field dependent masses, you find that at least if the masses are small, there's a kind of a Ginzburg-Landau type approximation to the effective potential or free energy as a function of the order parameter. And interestingly, there's a cubic term which is induced by bosonic fluctuations, and that could give rise to a first order transition. This is not true in general. In fact, in non-abelian gauge theories like the standard model, these simple methods fail. In fact, these non-perturbative techniques that I mentioned show that actually this bump is really only there for very weakly coupled scalars, which is not true in the standard model. The coupling constant is of order 1. So there's lots of recent work on calculating the effective potential in various theories, in particular the standard model plus extra Higgs, where there's a limited parameter space to look at. And to give you two highlights, one of which is that I noticed recently, or in the last couple of years, one of which is that sometimes one likes to use standard model effective theory and look at a phi to the 6th term here. That's not particularly accurate or reliable. It gives you a qualitative idea of how a phase transition might happen, but it's not good for reliable calculation. And the other is refining and sharpening up the techniques for calculating the reliable effective potential, which, as I understand it, the best way of doing it is this standard technique of dimensional reduction to a 3-dimensional effective theory, and at 2 loops, and then a 1-loop 3D effective potential. And this is all done for you now in this new software package, drAlgo or drAlgo. So what about strongly coupled theories? Well, of course, the standard model extension, whatever that is, whatever's beyond the standard model may be strongly coupled, and that's a big driver behind these ideas of composite Higgs. Higgs is a pseudo-Goldstone boson. So one is then inspired to look at phase transitions in for example, SUN Yang-Mills. So SUN Yang-Mills does have a first order transition, it's the confinement transition, but on the other hand, QCD does not. So the number and masses of quarks in the gauge theory do make a difference. And actually working out the parameters of these theories is rather difficult, even on the lattice. And for example, the thing that you really want to know is the surface energy of an interface, and that's actually not so well determined in general for general N. But nonetheless, one can try and use some models for the effective potential in these theories, which are this Polyakov model due to Pisarski, for example, which was used by these authors to have a look at the strength of the transition and then predicted the gravitational wave signal. And the general result was a little bit a bit negative, that the transition is too rapid to be strong. So it's rapid, the bubbles are small, and therefore the signal is weak. So another approach to think about strong coupling is, of course, holography, which is a very well-established technique to think about strongly coupled theories. And one way to think about them is to think about them. I mean, of course, the holography relies on the idea, the string theory-based idea, that a gravity theory in more than 4 dimensions, or with a curved 5 dimensions, 5-dimensional anti-de Sitter space, defines a quantum field theory in 4 dimensions. And one can build models, and certainly build models in 5 dimensions with asymptotically anti-de Sitter space, very simply, and by a suitable choice of potential, one can there's a particularly nice choice due to Bayer and Mateos a few years ago, 2 parameters which can give you first-order phase transitions. And, so we had a look at this model to see what phase transition parameters could be generated, and there's a satisfyingly strong first-order transition for a wide range of this the parameter space of this model, and also sound speeds which are not the ultra relativistic version. One can also use holography to work out the transition rate, and that involves working out the solution, the bubble solution critical bubble solution corresponding to the energy barrier. So there's a holographic way of doing that too. Well, one could of course find the bubble solution in the 5D theory, and this has been done at least for 2 space dimensions, but at the moment doing it in 3 space dimensions is too hard, because it's an entirely numerical procedure, solving this theory numerically. But one can also approach it holographically. One needs to not only calculate the effective potential of the dual theory that this this 5-dimensional model predicts, but also the kinetic term. And once you've got the effective potential and the kinetic term, you can make a standard computation of the transition rate. So we did this for a particularly simple model, and found again it's a similar story, that that actually the transition rates are a little bit too rapid, except for a sort of some small corner of the parameter space. So observability basically is this color. All right, so that was a little lightning tour of the microscopics or behind phase transitions. So phase transitions can happen in some theories, and so how do we work out some theories beyond the standard model? So how do we work out the gravitational wave spectrum that I briefly alluded to? So the way to do it is through hydrodynamic numerical simulations, first of all, and then to try and figure out what you're seeing and to build models. So we did some simulations some years ago now. It was quite difficult to get hold of the time you need quite large machines, tier 0 size machines to get the sufficient scale separation to to do these simulations. And the gravitational wave spectra kind of look like this. What do they look like? Well, they have a generic feature. They have a sort of a domed peak at wave numbers of around, wave numbers of around 10, or perhaps that might be 2 pi, divided by the mean bubble separation. And at high frequencies, there's a power law, which is well, actually, it's asymptotically k to the -3, although you might not see it immediately in a particular numerical simulation. On the low wave number side, it's a bit difficult to determine what any power law is, because you just don't have the volume in a numerical simulation. All right, so how can we understand this shape? What controls the wave number of the peak? What controls the power laws? What controls the shape around the peak? So it turns out that you can make quite a bit of progress by looking at a relativistic combustion theory and building a simple model based on that. So the expanding bubble of new phase can expand in one of 3 ways. One of which is the wall is slower than the sound speed. There's a pressure wave in front, and that's a deflagration. One of which it's a lot faster than the sound speed, and then there's a very sharp increase in pressure just behind the wall, and then with a trailing rarefaction wave. And then in between, there can be both a compression and a rarefaction wave. And this is all controlled by ideal relativistic hydrodynamics, because these are very large scales now that we're talking. We're talking a sort of 10 fractions of the horizon scale rather than microscopic scales set by the theory. The very interesting thing is that the radial fluid velocity and enthalpy distributions rapidly converge to a similarity solution. So that they always are functions of the radius of the bubble that it's got to at any time t, divided by the time since it was nucleated. And for example, a velocity the velocity in a deflagration plotted against this similarity profile could look like this for a wall speed of 0.4. So this is a relatively sort of transition of intermediate strength. About 10% of the thermal energy is converted from potential energy into available for the transition, wall speed of 0.4. Of course, if there isn't enough friction, and I'll come back to this, that can happen. The wall can continue to accelerate and run away to ultra relativistic velocities. So it may be that the velocity is not 0.4, but very, very close to 1. So building on this picture of deflagrations, detonations, and these intermediate hybrid states, one can build a model of what the velocity field looks like just by using linearity. If the transition is weak, these sound waves are linear, and so those self-similar shells become the initial states for the propagation of sound waves. And so then one just adds them up as a Gaussian velocity field. As time goes on, any particular region of space will be in the sound shells from more and more bubbles, and so the velocity field will get more and more Gaussian. So then that gives basically a very characteristic prediction. Even that, the characteristic prediction is that on the low k side, there's a very steep power law. On the high k side, it should be k to the -3. And that's entirely because the velocity fields are sharp-edged. And then there may be some intermediate power law if the shell is very thin, like here. Because then there are two scales, one of which is the mean bubble separation, and one much shorter distance scale is the shell width. So how does this do? Well, if you have as I said, in these transitions which are not too strong, so the sound waves remain relatively linear, it does extremely well for detonations. It reproduces the shape really well on the high, on the peak, at the peak, and the high K side. And the only two input parameters are these: the wall speed and the energy fraction released into the transition. So that's pretty good. Not so good for deflagrations, and I'll come back to that in a moment. Over predicts the signal, and also the large wavelength low K side. Well, you can't really tell what's going on. So, by the way, these are graphs of the growth rate of the transition. So one rather than the actual gravitational wave power spectrum at any particular time. So it's the change in the gravitational wave power spectrum, which is the actual prediction of what this model does. And it's been scaled by the mean bubble separation to get, well, that's the natural scale to choose. So the question of what this low K power law really is still an open one. There's been some recent advances in simulation, which enables one to do larger simulations, or rather to have a larger dynamic range. But the simulation is still probably not run long enough to really see this K to the 9th power law. So, what are the things that are missing? And basically, it's non-linearities. And so, if you go to slightly stronger transitions, you find that the energy released, at least in a deflagration, the energy released heats up the fluid in front of the expanding bubble and reduces the pressure difference. The bubbles slow down and eventually leave behind a bunch of shrinking droplets. Actually, there are self-similarity solutions to these droplets as well, but they don't add to the kinetic energy of the fluid. So that reduces the kinetic energy, and is probably the reason for this difference. So and it can reduce the kinetic energy by quite a lot. Here, by factors of 100 even. So the next important non-linearity that we need to consider is the non-linearity in the flows of the fluid during and after the transition. So, for example, when again in deflagrations, the interaction between the fluid flows flowing through the bubble and the bubble wall generates some vorticity. So these are you might not be able to see because the font is rather small here, but these are all vorticity that we're looking at. So where the bubble has collided leaves behind some a kind of a ring of a sheet of vorticity. It's also possible that vorticity is generated by collisions of shocks, which was proposed by Penn and Turok, but this effect actually turns out to be small in our case. So this, but in a strong transition, you might expect to generate the stronger the transition, the higher the vorticity. And so then you have to start thinking about decaying vortical turbulence. And that's quite a complicated story, which I think still hasn't been solved yet, but is the latest chapter in the development of understanding of gravitational wave production, which is again numerical simulations combined with analytic modeling from earlier this year. And you can see that the thing that you can certainly say is that on the low K side, the power spectrum is K cubed, so a lot lot shallower than K to the 9. It's essentially white noise. That's what the K cubed is, the definition of the power spectrum. But there's a sort of a complex evolution of the shape, which depends on the strength of the transition, the velocity, therefore the velocity of the RMS velocity of the fluid that emerges from it, and also the size of the bubble or the size of the fluid flow in units of the Hubble. So this is the psi is the characteristic length scale of the flow. So then, what else? Okay, so actually one of the key forms of nonlinearity is in the form of shocks. So in fact, shocks will develop eventually from any sound wave. So even if you put in a lovely sine into your fluid, eventually a shock will develop, and it will develop on time in time with the length scale of the flow, so the wavelength of the sound wave divided by its RMS velocity. Shocks have a generic feature in that they will induce a velocity power spectrum of 1 over k at high k in any number of dimensions, and which means that one can actually look at shocks in 2 dimensions and apply the understanding to 3 dimensions, which is what we did last year. And what we can gain from that is an understanding of how the kinetic energy decays, because the shocks are dissipative phenomena. They generate entropy. So the kinetic energy decays, and as the shocks decay, the length scale between them grows. The sort of the shock density decreases, and so as the shock scale evolves, the shocks are generating gravitational waves on larger and larger wavelengths, and so you get this intermediate power law you can get an intermediate power law, which we predicted to be k to the 5.5, but that prediction depends on the idea that you can really take the 2-dimensional model into 3 dimensions. So that's being checked at the moment. And one of the things that is kind of most exciting, and I know is of interest to many people in the audience, is what happens at really, really strong transitions where we haven't gone yet in numerical simulations. So strongly supercooled transition where the thermal energy grows as the universe expands. The thermal energy gets smaller and smaller, and eventually becomes much less than the vacuum energy, and inflation, some thermal inflation, takes over. So if there's not much plasma about, there's less friction, and the wall accelerates until you get lots of particle production at the domain wall, at the phase boundary itself. And there's some puzzle about what exact Lorentz factor is achieved. There's the sort of majority opinion seems to be that the Lorentz factor scales roughly as alpha, the ratio between vacuum energy and thermal energy. But there's a dissident group who think that it's the square root of alpha. And actually nobody's really been able to convincingly determine one or the other. And there are some reasons, in my view anyway, for favoring this top one. So if the bubbles collide at while they're still accelerating, all the energy of the transition is in the bubble walls, and you want to look at the collisions of scalar field bubbles, and you get something that can look like this. Here, these are the waves in scalar field as the bubbles collide, and you get power spectra that kind of look like this. Some characteristic power law which is steeper than the -1. And there lots of work on this recently. You get this slope has some information in it. It tells you something about whether the wall is thick or thin in the jargon, and also tells you, it can distinguish between whether or not the order parameter is a gauge singlet or a gauge multiplet. So so then the question is, if if the fluid takes over, eventually the wall reaches steady state and is surrounded by one of these extremely relativistic hot fluid shells, then what happens then? Well, a couple of groups have as a first step have assumed that, well, fluid shells pass through each other at weaker transitions, so why not do these strong transitions? And then one can make some predictions for the gravitational wave power spectrum. And again, you get some characteristic power law on both sides. And this is not just an academic, well, of course, it is an academic exercise because we're academics, but the strong supercooling occurs naturally in a class of model which are very interesting from the point of view of addressing the hierarchy problem. These are classically conformal or nearly conformal standard model extensions. And these ones are kind of safe against the old graceful exit problem of inflation because eventually they will make they will transition. The phase transition will happen at some temperature. If the bubbles don't nucleate in time, there will always be some quantum destabilization at the end. In which case, all this doesn't happen, and instead you get gravitational wave generation by the standard inflationary mechanism. All right. So in the last few minutes of the talk, I just want to say a couple of things about what we might see and how we might observe it. So if the sound shell model provides a reasonable guide to what kind of parameter dependencies one might see, then this is how gravitational wave spectra will look, and how they will depend on, for example, nucleation temperature. That's very simple. That's just an overall shift in frequency. How they depend on the energy release parameter, alpha. The amplitude goes up and down, but actually the shape changes a bit as well, because the shape of the sound shell around the expanding bubble changes. If you change the mean size of the bubble, then actually both the amplitude and the frequency changes. So the wavelength of the gravitational wave changes, but also bigger bubbles are more efficient at making gravitational waves. And then finally, if you change the wall speed, you really change the shape of the sound shell, and that really shows up in the gravitational wave spectrum. And so here you have an extreme case where you have a very, very narrow shell, and that's why there's features at higher frequencies. Of course, looking for those power spectra, there are lots of foregrounds generated by astrophysical objects, and the main one to worry about from the point of view of phase transitions is white dwarf binaries in our galaxy, and they will probably produce some kind of confusion noise which will interfere with looking for a phase transition. On the other hand, this confusion noise, looking on, is another way of plotting it in terms of, not in terms of strain, but in terms of gravitational wave power. This confusion noise is annually modulated because it's in our galaxy. And so there's a good chance that it's anisotropic. So it's a good chance that this will actually be quite easy to separate from the phase transition signal. So one can make some very rough estimates of what's detectable by looking at the Fisher matrix. What's the Fisher matrix? Well, it's the inverse of the covariance matrix of the signal to noise ratio. So if you have some parameter theta and your signal depends in this way on theta, then this is the inverse. This is the curvature of the likelihood at the peak of the likelihood. And the eigenvalues of this covariance matrix give you the uncertainty in the parameter theta. So these parameters in this very simplified model are wall speed, energy release, bubble size. Actually, the lower R star is bubble size in Hubble units, and nucleation temperature. And you'll see that the main message is that the wall speed is likely to, if the signal is detectable, the wall speed is likely to be the best determined parameter. And that's understandable because the wall speed makes the biggest difference in the shape. Okay, so coming to the end now, I just wanted to mention an interesting possible skeleton in the theory cupboard, and that's to do with all this business of bubble nucleation is all well and good, but what evidence do we have that this theory, which in condensed matter systems goes under the name homogeneous nucleation theory? What evidence do we have that it's actually correct, that we can generate through thermal fluctuations these incredibly rare configurations? So there is a system where homogeneous nucleation theory makes a prediction, and that's in the AB transition of superfluid helium-3. And this is very well understood theoretically and very well studied experimentally. So, for example, here's the phase diagram in terms of temperature and pressure. Here we have the normal Fermi liquid, and then we have the superfluid transition. This is the solid line, and then there are two different phases with two different unbroken symmetries: the A phase and the B phase. So this is sort of like a standard model phase transition with a two-step transition. You could think of it in that way. And here is the latest theoretical calculation of where this line should be, and it's incredibly good. This is it lines up with the experimental values extremely well, and this is as a result of working out. Basically, it's an effective potential calculation using couplings which are evaluated from or constrained from normal fluid measurements. So in this theory, if you compute the transition rate, you get that the exponent here, the energy barrier in temperature units, is about 10 to the 6. So once you reach 10 to the 6 in the exponent, you cease to have to worry about what the units are, because if you express it in terms of seconds or years or ages of the universe, e to the 10 to the 6 is basically the same number. So supercooled A phase should last a long time, but the AB transition is observed time and time again in experiments, despite experimentalists trying to eliminate sources, for example, ionizing radiation or boundary effects, rough surfaces in the apparatus. And there are some more exotic theoretical possibilities that have been proposed. Many particle physicists and cosmologists have taken an interest in this system. So, in response to this this puzzle of some cosmological theorists got together with condensed matter experimentalists, Royal Holloway and Lancaster universities in the UK, in a project called Quest DMC. This stands for something like quantum enhanced superfluid technologies for dark matter and cosmology. This is the cosmology. Superfluid helium-3 is actually a very good light dark matter detector as well. So that's another set of experiments. Okay, so I will wrap it up there. The gravitational waves will be probed from a possible electroweak transition. Will be probed by LISA and other space missions from the mid-2030s onwards, and they will be able to measure, or well, hopefully measure, but mainly constrain, probably, phase transition parameters. And if a signal is observed, then one of the messages is that the wall speed is likely to be the best determined. And the idea is that that will help us constrain parameters from any underlying particle physics models that we are focusing on at the time in the light of LHC and other particle physics experiments. And so in order to make this a possibility, we need to go more accurate calculations of gravitational wave power spectra from these underlying parameters. So that it certainly means understanding these nonlinear effects in the fluid, and also particularly in these highly shocked fluids that you get in the supercooled transitions, and also to sharpen up our calculations. I'd say that the main target is to get the reliable calculations of wall speed, and that's a hard problem because it involves non-equilibrium quantum field theory. And so these are the sort of areas in the ambition which one could have in this area of making gravitational waves a good probe of the electroweak era, as the cosmic microwave background is for the decoupling era and hence inflation. Okay, thank you very much.
Okay, thank you, Mark, for a very nice overview. So we have lots of time for questions. You can just unmute or raise hand. Any questions for Mark? Yeah, Joachim has a question. Please go ahead.
Hi, thanks for this super interesting overview talk. So you mentioned that for supercooled phase transitions, the simulations are not quite there yet, being able to simulate those. So what would it take to move further towards the supercooled regime in the simulations?
Yeah, it's something that we're working on right now. I mean, the main difficulty is technical one, in that in a supercooled phase transitions, you have larger and larger gradients in the energy density and the fall velocity, and this is sort of I mean actually it's stuff that people in the astrophysics community have to face as well when you're talking about relativistic jets. So it kind of takes time is the main answer. We can certainly push to I think we can push to regimes where with our current state of the code, to regimes where the thermal energy is greater than the vacuum energy, but probably not much greater. To get to these, I think to get to these enormous ratios, that'll never be possible numerically, and you probably need some analytic understanding, which hopefully will be gained by looking at these strong numericals and shocks and so on.
In the current simulations, are you working with a fixed mesh, or is this an adaptive mesh already?
It's a fixed mesh.
Okay.
Yeah, it's not clear that adaptive meshes are worth the extra trouble, although it's becoming simpler and simpler to use them. Essentially, because you really want to because the structure throughout the whole volume in the form of these shocks and waves. So you.
Okay, I had been thinking about the bubble walls, thinking that maybe the most interesting physics is happening around the bubble walls, so a finer mesh there might help. But of course, that's only true until the bubble walls have collided, and then it's, as you said, things are happening throughout the volume, right?
Yes. I mean, it's certainly, yeah. I mean, I've seen there've been sort of interesting. There's been interesting work using adaptive mesh simulating topological defects where there are similar problems. So I think it may be a profitable avenue to pursue.
Okay, thanks a lot.
Any other questions or comments? I don't see any. Then may I ask a question? So assuming that the simulation results are for single-state phase transitions, how well we can apply them to, say, two-state phase transitions for the spectrum part? Can we apply independently, like for the two steps, or?
That's a good question. I think, yes, you have to, I think probably you have to assume that all basically all the sound waves have died away before you can apply them independently. So that puts, and you can estimate that on the basis of this non-linearity time scale. Then before that, you get into this interesting regime where you have pre-existing temperature fluctuations, and where it's colder, that there will be preferential phase transition happening there. So the sort of and that has been looked into, although not necessarily in the context of a two-step transition. It's an interesting, it would be an interesting area to explore.
Any other quick question for Mark?
So I have a question.
Yeah.
Hi, Mark. Regards to the fact that you gave some comments about phase transitions regarding strong coupling, and you're like saying that okay for the community to, let's say, come forward in regards to the bubble wall velocity, what, let's say, intended approaches there, since in regards to, let's say, the QFT let's say part would already be quite difficulty, and you have the, let's say, recent approaches, let's say by David Mateos and these guys when they work on like in ADS and actually do, let's say, this for simulations in ADS by using ADS CFT. Do you have any, I don't know, let's say, would you have any other kind of, let's say, ideas in mind of what could be, let's say, I don't know, an idea to tackle it?
Yeah, I mean, I was going to talk a little bit about wall speeds, but then I realized I didn't have enough time. But the main techniques that people are using is the Boltzmann equation. So there's quite some success in tackling the sort of the problem of the top quark pressure using Boltzmann equation, because it should work reasonably well. And indeed, if you have a weak transition, then linearized Boltzmann equations can give you a reasonable answer in to the friction. There's been a lot of good work recently on that by Jim Klein and his collaborators. Beyond that, there are a couple of problems. So, for example, the problem of the pressure from the soft modes of the gauge field, that's a tricky one, and I think that can only be solved by experts in soft modes, which is again, luckily here in Helsinki, right down the corridor, Kari Ruumokainen, who is an expert in that, the simulations of soft non-abelian gauge fields. But then, at some point, probably you'll have to, go beyond the Boltzmann equation and sort of tackle it with, the next layer in quantum field theory, which I guess would be full, two-particle irreducible non-equilibrium quantum field theory. These are all probably all difficult ideas, because if they were easy, then somebody would have done them.
It's fair enough. Since I don't know, part of a follow-up to it, since let's say when you look at doing the transition, regarding electroweak cases, you care, let's say, a lot about the reflection transmission when you, let's say, enter particles entering the wall and being and if I were to think of this like in strongly coupled cases of, let's say, I don't know, if you do it in pure gauge, so you would have, let's say, the gluons, because then you could think about, let's say, actually having several gluons hitting, let's say, the wall, provided you would produce glue balls in your confined phase. Could one, let's say, think in a sense of, let's say, the amount of momenta or something like that you would need in regards to overcome the threshold of the fact that you would produce glue balls in the confined phase? Could that be, let's say, something as a let's say, I don't know, as a first estimate or something in these theories?
I think so. Actually, I've just noticed a comment in the chat from Jan Gutnoir, who actually, I think, if I'm right, sort of had a look at a model like this. Basically, you can, as you say, that the energy the momentum transfer from forcing gluons to turn into glue balls it generates a pressure. So yeah, if you search for his name.
Okay, we're running out of time. So
all right, thanks,
maybe we can.
Thank you.
Yeah, Marek has a question.
It's not a question, just a short, announcement, maybe reminder from the organizers that this is a very interesting discussion. But we will actually have a devoted discussion session at 6 p.m. So I hope all of you can attend, and then we'll continue on with this. Thanks.
Yeah, I'll answer the question in the chat in the chat, so we can carry on.
All right. So let's thank Mark once again. So next speaker is Michael Baker. So Michael, are you there?
Oh yes, I'm here. I'll just share my
okay. Yeah.
Okay, hopefully you can see my slide on the screen.
Yeah. You have 30 minutes, so maybe I'll give a reminder when you have 5 minutes left. So over to you.
Great, thank you very much. Okay, so it's a pleasure to be here, and I'm going to talk about some of the things that BSM phase transitions can impact in the early universe, and I'll talk in particular about novel production modes of dark matter and of primordial black holes. I have to apologize, I'm going to have to skip the discussion session. I'm in Melbourne at the moment, and the local time is 1:30 in the morning. So I won't be able to stick around too long, but it's a pleasure to be here nonetheless. Okay, so the outline of my talk. I'll first talk about the impact of phase transitions on dark matter production, and I'm going to talk about two novel dark matter production mechanisms. The first one is a kind of a family of mechanisms. I'll give one example, we call that thermodynamic dark matter. And the second one is called filtered dark matter. After the dark matter section, I will talk about primordial black hole production. And we'll see how the filtered dark matter mechanism can be sort of modified slightly to give a production mechanism of primordial black holes. And then at the very end, I'll just make some small comments about connections to gravitational waves. Okay, but first I'll talk about phase transitions in dark matter production. So there's a bunch of evidence for the existence of dark matter. Maybe some of the first seen was the galactic rotation curves. So here we see the triangulum galaxy, which is the second nearest spiral galaxy to our own. And if we take all of the mass in the stars and the gas, add it up and calculate what we expect the rotation speed of the spiral arms to be at various distances from the center, we get this dashed gray curve. But then observations give us this curve up here. And so we see there's a huge discrepancy here, which can be explained if there's some non-visible matter in the galaxy. So this is one of the evidences for dark matter. There's also strong evidence from gravitational lensing, such as bullet cluster, and also from structure in the CMB and simulations. And so from all this evidence, we now know that dark matter exists and it's stable, at least on the lifetime of the universe, a bit longer. It has to be stable. It's cold. And so this means that if it's a particle, it's moving non-relativistically today. It's dark, and so there's very strong limits on its interaction with photons. It's not one of the standard model particles. And thanks to observations of the CMB, its abundance is known very accurately. So the favored explanation for a long time is a new fundamental particle, which has been produced via thermal freeze-out. And there's been a very significant experimental program looking for this over the last 20, 30 years. And it hasn't been discovered yet. And in this first part of the talk, I'm going to explain how phase transitions may explain how dark matter could be there but not have been discovered. And we're going to be changing the production mechanism away from thermal freeze-out. Okay, so that brings me to the first production mechanism, thermodynamic dark matter. So this is a kind of quite a general idea, and we explored a variety of different sort of concrete mechanisms. I'm going to talk about one of these today, but there's a bunch of these discussed in these different papers. The kinds of models that they'll appear in are quite broad. I'm just going to take a kind of simplified picture where we just introduce 3 new fields. There's going to be a new scalar, and this is going to undergo a phase transition where it obtains a vacuum expectation value at some temperature. And so that's this field S. There's also we're going to introduce 2 new fermions. There's going to be chi, which is going to end up being dark matter that's charged under some stabilizing symmetry, we assume. And some partner fermion psi, which is also in the dark sector, but somewhat heavier than chi. Right, so I'll just go through one of these mechanisms today, just to give you a flavor of the kind of thing that I'm talking about. So in a phase transition, the scalar field S, if we look at its effective potential, at high temperatures, its minimum is a 0 field value, and then as you go through the critical temperature, it obtains a VEV. Here we're looking, this depicts a second order phase transition, but it can also, these kinds of mechanisms also apply for first order phase transitions. We also do some things with 2-step phase transitions. So there's a range of different phase transitions. Here I'm just going to exemplify it with a second order phase transition. So here, if we look at the vacuum expectation value of the new scalar field S in blue, as temperature reduces, that's time going left to right in this plot. It's going to be 0 for a long time, and then at some critical temperature, it jumps up to some non-zero value. But then I've also put on here the mass of the scalar. So the mass of the scalar is given by the second derivative of the effective potential at the phase the universe finds itself in, here just at the minimum. And we see that it starts off quite high from large finite temperature corrections, and then shrinks as the temperature reduces. And then through the phase transition, there's a period where it's very, very small. And then it sort of goes up to its final value, which is the second derivative of this 0 temperature minimum. And so this first mechanism kind of hinges on these 2 observations, that the expectation value of the field grows, but also the scalar mass evolves dynamically through this period. So here I'm plotting for a certain choice of parameters, the masses of some particles as a function of the temperature. And we're going to imagine that this chi couples to S weakly, so that its mass doesn't change, it just has some value. Whereas the psi mass couples to S more significantly. So it starts off lighter than the dark matter, and then it gets a contribution from the SVEV, just from the usual Higgs type mechanism, just from the expectation value of the S. And that gives a contribution to the mass of the psi, and it ends up being heavier than chi. In red, I've plotted the mass of psi plus the mass of S. So that's the red line. So we have this reduction and then a jump. And we can notice that this 1-to-2 process, so chi decaying to psi S, or the inverse decay, psi S going to chi, this is kinematically allowed between T start and T end, but it's not allowed at higher temperatures. And kind of crucially, it's also not allowed at 0 temperatures. So then if we go along to compute a variety of processes, look at their rates in the early universe and compare them to the Hubble rate. If we ignore the finite temperature effects, that's the dashed line, we would only really look at the 2-to-2 process. Chi S goes to psi S as a depletion mechanism of chi. The chi to SS process for these couplings we assume to be small. So that the dominant annihilation process would go through a kind of co-annihilation mechanism where chi first converts to psi, and then psi to SS. This is an equilibrium for the whole period, so you sort of lose the energy density from chi from that way going to psi, and then psi goes to S, and then S goes to the thermal bath. So if you ignored the finite temperature effects, you'd only consider this process, which is the dashed line, which we see is always below Hubble. But then taking into account the way the mass changes through this process, that affects the 2-to-2 process, and we have a bit of a resonance behavior as particles go on and off shell in this process. But then also kind of crucially, this 1-to-2 process opens up. And now this just has one small Yukawa coupling. So this has a large rate. And you can see that this is the dominant rate. And so if we look at how this can impact the yield of chi through this process, the yield is roughly the number density of chi divided by the number density of photons, more or less. So the equilibrium number is this dotted line down here. So when the temperature is roughly equal to the 0 temperature mass of chi, we start with a large abundance, and then it sort of exponentially reduces as the temperature becomes lower than the 0 temperature mass of chi. In the usual thermal freeze-out story, if we didn't know about these finite temperature effects and we just took everything at their 0 temperature values, for this choice of parameters, we'd freeze out when chi is still relativistic, and we'd end up with far too much dark matter. However, taking into account this sort of complicated behavior of the masses and this opening up of the 1-to-2 process, we first leave equilibrium, but then when at T start, when the 1-to-2 process opens up, then we come back into equilibrium from some time, follow the equilibrium curve until T end, when this 1-to-2 process becomes kinematically forbidden, and then dark matter can freeze out. We see here that there's kind of roughly 10 orders of magnitude difference in your estimated dark matter abundance if you take into account the finite temperature effects or if you ignore them. So this is a kind of a case study proof of principle where to demonstrate that these kinds of effects can be really important in the early universe, and a point in parameter space which you would normally think has no chance of giving you the observed relic abundance actually can, because of this sort of dynamic behavior of the masses through the phase transition. A kind of maybe an interesting point of this mechanism is, in contrast to the usual thermal freeze-out story, where the final abundance depends strongly on the interaction strength between your particles, here the abundance is determined by the temperature that this 1-to-2 process ends. So it's actually pretty independent of the coupling, as long as your assumptions are satisfied. And it's just the temperature at which this kinematic threshold closes, and then you very quickly freeze out. So the abundance depends on a different set of parameters to the ones you normally think of for dark matter production. Okay, so I'm not going to say much more about this story. There's a variety of mechanisms. We have the kind of variety, like variations on this idea. But just because I want to cover a few different aspects in this talk today, I'm going to go on to the next mechanism, which is filtered dark matter. Yeah, okay. Sorry, I just saw that there's some chat, and I was checking that, not to do with me. Okay, filtered dark matter. So here we have, this is a different dark matter production mechanism, which really depends on a first order phase transition. So we're going to have bubbles nucleating, bubble walls passing through space. Here we have a simpler picture where we just have a new scalar field which undergoes a first order phase transition and a dark matter candidate chi. And so here I'm drawing the two phases. We've got the high temperature phase with 0 VeV and a massless chi on the left-hand side. And on the blue is the low temperature phase where the scalar field has obtained a VeV. And we're imagining that the new part, the chi, which is going to end up being dark matter, this obtains a mass due to the Higgs mechanism again, which is somewhat larger than the temperature. And okay, we have the picture where we have a bubble ball that's here traveling from right to left. So on the left-hand side, we're going to start with a relativistic abundance of chi, and we can ask what happens when it interacts with the bubble wall. And there's going to be two cases. If the momentum is larger than the change in mass between the two phases, then the particle will be able to travel into the ball and into the bubble, and its momentum will be somewhat reduced. However, for lower momentum modes, energy conservation will mean that it doesn't have enough kinetic energy to convert into the rest mass energy it would need, and it ends up being reflected from the bubble wall. And then it can be reflected and absorbed back into the plasma. So this is, in this cartoon picture, going to be the mechanism which reduces the dark matter abundance for us. It's going to be most of the dark matter is reflected and absorbed back into the thermal bath, where just the Boltzmann tail that happens to have high momentum is allowed to pass into the, or has the energy to pass into the bubble wall. So it's the exponential suppression in the Boltzmann tail which does this 10 orders of magnitude reduction in the dark matter abundance. So that's the cartoon picture. To actually solve this, we numerically solve some Boltzmann equations. We introduce ansatz, which is like motivated by the symmetries of the problem. We integrate over some unimportant variables, which are again motivated by the symmetry of the problem. Assume steady state, because here we're just looking near the bubble wall. And we end up still with quite a complicated partial differential equation, but we figured out how to solve this using a result from mathematics method of characteristics. Turned out to be a nice way to solve the resulting partial differential equation. And so what we see here is sort of the momentum space on the y-axis versus physical space on the x-axis, and this opaque region in the middle, this is the bubble wall where the VEV turns on from 0 to its final value. And so in the top left corner of this parameter space, these are particles with high momentum that are impinging on the bubble wall. And we see, as we saw in the cartoon picture, they pass through, but they have a reduction in the momentum. Low momentum particles, on the other hand, are reflected from the bubble wall. And the color coding tells us sort of the density of the phase space distribution function at each point. White is the equilibrium value. And then we see, particularly here on reflection, we have a build-up of particles. But then, okay, it's not in the plot, but if you continue further in front of the wall, they're absorbed back into the plasma. So if you go far enough to the left, it'll be white again. And you have a certain amount that has made it into the bubble. You can then integrate over the momentum in the Z direction deep inside the bubble and calculate the final yield, or the abundance of dark matter. And so we do that calculation, and we then specialize just to points in parameter space where we obtain the observed relic abundance, and we look at the dark matter nucleon direct detection cross section. Here we see some of the slightly old limits now, and the neutrino floor. And this purple region is the region that this filtered dark matter mechanism can populate. We have this little island out here, which is it's almost all been probed. But this main bulk is quite interesting for two reasons. It's going to start to be probed, or is starting to be probed right now, and will continue to be probed over the next few years. But also a nice feature is there's a thing called the Gries-Kamienowski bound. So for thermal freeze out, just because of perturbativity of the couplings, you can't go larger than a few hundred TeV in mass for the dark matter candidate. But now here, because we've got a very different dark matter production mechanism, we can easily go to heavier masses, and sort of this peak over here, which is starting to be tested now, is a way of producing dark matter beyond the Gries-Kamienowski bound. So that's a sort of interesting motivation for looking at heavier dark matter candidates than are usually considered. I'll just skip over this very briefly, but just to say, we also extended the model in a way which can also do baryogenesis at the same time. So you introduce some chiral elements to the extra chiral elements to the theory, and then you end up with asymmetry in the lepton, the chiral asymmetry of the leptons, which can then be reprocessed via follow-on processes into a baryon asymmetry. And in our model, we've shown that we can get the observed dark matter abundance and the observed amount of baryogenesis in this band. So this is just quite a small band, but this depends on, there were some assumptions that we had to make, which meant that some couplings had to be quite large, which sort of constrained us to this band. But we think there's no reason why we couldn't do both filtered dark matter and baryogenesis in the whole region. And we just need to extend our framework a little bit to show we can do that. But with our current framework, we can't make accurate calculations in the bulk of this region just along this band. Okay, so that's what I wanted to say about dark matter. I'll now briefly talk about primordial black hole production. So just to say, black holes are very interesting for a variety of reasons. We're now certain they exist. We've seen the binary and spiral mergers, and we've seen direct images of their event horizons. These black holes, which have directly been observed so far, are solar mass and supermassive black holes, but there's reasons to also think about primordial black holes. So these are lighter black holes, which may have been, or they may be heavier, but yeah, primordial black holes these are black holes that formed very shortly after the Big Bang. And some reasons to think about these are that they could remove unwanted monopoles or domain walls. They could be seeds for the supermassive black holes that we've seen, or large-scale structure that we also see in the universe. And in certain regions of kind of their parameter space, they could possibly also be dark matter. Now, there's a variety of existing production mechanisms for these. But we propose a new production mechanism sort of based on this filtered dark matter scenario. And just because it's somewhat different to some of the other mechanisms, some of the other mechanisms are maybe a little bit fine-tuned or so on. Yeah, I mean, it's always good to have new mechanisms, and in certain setups, our mechanism may be favored. We've seen people citing this for us already, that they prefer our mechanism because it fits better with their existing setup. Okay, so we're back to this picture of what's happening to a new particle that's interacting with a bubble wall in a first order phase transition. And we kind of ask the question, what happens if chi, when it's reflected, if we're in a different region of parameter space, so it's not absorbed back into the thermal bath, but it just builds up on this side. So now we're in kind of a quite different situation. We can't just focus on the physics near the bubble wall. We have to kind of go to a larger region in space, in physical space. And so here we see a kind of a pocket that's shrinking. So this is late during the phase transition when there's many bubbles are colliding and you have a pocket that's shrinking. And again, we have this chi particle that's just building up in this region. And the idea is that the energy density associated with this chi, we wanted to see whether that alone could be large enough to trigger a black hole formation. And so we again numerically solved the Boltzmann equations, but now it's considerably more complicated. We have to retain two momentum directions. We have to keep the time dependence, and we need to solve in the whole volume, not just near the wall. But we did that. And then here we plot the energy density in chi, the average energy density over a shrinking pocket, as a function of the radius of the pocket. So again, time is going from left to right. And we ask when the energy density in the region is the Schwarzschild radius of that energy is larger than the region itself. That's this gray triangle at the top. And we see that for certain parameter points, and in fact, a large range of parameter points, we satisfy this bound. And so at that point, you just can't stop black hole formation anymore. The other curves, we looked at what happened if you go to, there's interesting reasons why this can fail. And so here's a parameter space plot of, in gray is the existing constraints on the basically the number density of black holes versus the mass of primordial black holes. We see this is a very large plot covering many orders of magnitude. And just to say that our mechanism, depending on the temperature at which it happens, given by the top axis, and these diagonal lines, this P is the probability that a black hole forms in a given Hubble volume. So depending on that probability and on the temperature, we can basically fill this whole parameter space. And so there's existing constraints in gray, but also interesting regions like this green region could seed supermassive black holes of large scale structure. And this blue line, black holes could be all of dark matter. Okay, great. Right, so that's the new production mechanism of primordial black holes. And now I'll just say a few things about gravitational waves. I don't have too much to say because we haven't yet made predictions for the gravitational wave signals expected in these kinds of phase transitions. So in the first part, I talked about this thermodynamic dark matter. These phase transitions, as I said, may be first order or second order. So if they're second order, we don't expect a signal. But when they're first order, we would, and maybe that's detectable, and that's would be good to look at the kinds of gravitational wave signals we predict. But the filtered dark matter and this new primordial black hole production mechanism, they really rely on, sorry, that's a typo, rely on a first order phase transition. So here there's maybe a stronger connection between the mechanisms and the gravitational wave signals you may expect from that. However, in these mechanisms, we find we typically require some supercooling. And yeah, that's a kind of a challenging environment, as we heard in the first talk, to do calculations. And we found trying to code this, the existing code is somewhat unreliable. So that's one of the reasons that we haven't really finished this yet. But we hope to make progress in connecting the phase transitions to gravitational wave spectra. Okay, so coming to my conclusions. Phase transitions can have a dramatic impact on the production of dark matter and primordial black holes. And it's one of our interesting directions to explore in the future is to look at the connection to gravitational wave signatures. Okay, thanks. I'll end there.
Right. Thank you very much, Michael, for a nice talk. Do we have time for questions? Please unmute and ask.
Yeah, may I ask a question?
Yeah.
Yes, thanks for the talk. I was very interested in the models you put forward, and I'd like to ask about this last one, about the black hole formation. And I was wondering, is the chi particle scattering and behaving hydrodynamically in that bubble, or is it just sort of rattling around?
So we take a kind of a particle physics point of view on this. So when we solve this Boltzmann equation, where did I put that? This Boltzmann equation. And so on the right-hand side, we have a collision term here. And in this collision term, we take account of scatterings and annihilations and production of the particle. So we don't just take a fluid approximation, but we really, so as we're tracking the phase-space distribution function, that allows us to calculate this collision term. So take account of scatterings and annihilations.
So I guess my question then is, what is the scattering length in relation to the size of the bubble? Because if the bubble is much bigger than the scattering length, then you'd expect it to behave hydrodynamically, I guess.
Yeah, when we did this, we broke it up into two different regimes. So we had one regime very close to the bubble wall, and another regime in the bulk of the bubble. The scattering length, of course, it depends on the coupling that we take, and we look at quite a large range of Yukawa couplings for that particle. But I think typically for the typical range, we look at the scattering length was much shorter than the radius of the bubble.
So that's sort of a bit puzzling, because then the hydrodynamic behavior of a shrinking droplet is in fact I sort of alluded to it, and that's kind of known, and sort of the heat kind of leaks out, and there's no sort of build-up of density in the center. So, but it may be that there are some solutions which have the sufficient density inside for.
Well, so the special thing that we're adding is this chi particle really gets a large mass outside, and its mass is something like 10 times the temperature. And that's the thing that's trapping this particle inside. So actually, a lot of the effect of this increasing energy density is really just from the fact that you're taking these chi particles that were spread out in space and sort of compacting them and just putting them in some small region. And so it's just so it turns out to be an R to the fourth scaling of the energy density. 3 of those powers come from just really shrinking them into a small pocket in space, and then you get 1 extra factor from every time the particle bounces off the wall. It's you gain a little bit of energy, and that's the extra factor in the R to the fourth scaling. But I think that's the extra ingredient we're adding that you don't normally have in a first order phase transition.
So does the kind of the pressure then not build up so that it stabilizes the whole droplet?
Right. So this is something that we worried about quite a lot, and exactly how so at the beginning, so the pressure has to be large enough so that you can keep shrinking all the way until you get sufficient energy density. And as the population of Chi particles build up, you get an increase in pressure from that population of Chi particles. So you'll have an accelerating bubble wall velocity at the beginning, because you need to be in a situation where just the latent heat from the phase transition leads to a large pressure imbalance at the beginning. You have an acceleration of the bubble walls, and then at some point, you kind of want that always, because you want the pressure from the phase transition to always be larger than the outward pressure from the Chi particles. You want quite a large pressure there. But you also want to make sure that the walls don't become fast enough that as they become more and more relativistic, it sees a boosted population of Chi particles. And then in that frame, they could then have enough energy to pass through the bubble wall. So there's a bit of a balance there to make sure that, I think we're always going to be a situation where the wall is accelerating, at least in the beginning of this, but you don't want to accelerate fast enough that you get so ultra-relativistic that the Chi particles can then leak through. And so, I think we appealed that maybe kind of other mechanisms could come in to limit the bubble wall velocity, like transition radiation, something like this. But so there's definitely an interesting story there that we would like to explore further about exactly the evolution of the bubble wall velocity and so on.
Thank you.
All right, we're running out of time, so let's thank Michael once again. So our next speaker is Graham White. Graham, are you there?
Yes, can you hear me?
Yeah, you can share your screen maybe.
Yes, okay, so I hope that there's everything's okay. My child's trying to get to sleep in another room, and two other kids are trying to get to sleep in the room. This is the only room I could find. It's quite late here, but hopefully we can proceed, no worries. Okay, so should I just proceed, or is it introduction?
Yeah.
Okay.
Yeah. Go ahead.
Okay, so this is a paper based on recent work, which was done with one student, which is on the postdoc market. So if anyone's looking for a very talented postdoc who's quite technical, that's Jyotimir Roy. And it's on using a different method, which is of basically doing finite temperature perturbation theory. Okay, so the main motivation for this is, of course, gravitational waves. It's a major feature of our workshop. And what's so exciting about the gravitational waves is it's the only method we have to really look at what the universe was like in the first second. When the universe was 1 million years old, we can look at the last light, which is CMB. The universe was about 1 minute old. We can look at the first elements produced. But gravitational waves is pretty much unrivaled for looking earlier. And of course, the theme of this workshop is we're looking for looking at gravitational waves from strong first order phase transitions. And of course, how this works is is you imagine there's some system with a true and a false vacuum, where as the universe cools, eventually becomes energetically favorable to go from the trivial vacuum to a vacuum which breaks some symmetry typically, and if there's a barrier between the true and false vacuum, then this doesn't happen smoothly, but this occurs through bubble nucleation. And essentially you have 3 contributions typically to this to the gravitational waves, which come from this violent process of the universe boiling. The first comes from the scalar shells colliding, which are you need really relativistic walls for that to happen. Of course, in Warsaw, there's experts, which I'm sure will tell you more about this today. Then you also have the sound wave contribution, which Heinrich very nicely summarized. And then, of course, the turbulent contribution. I believe there's some fairly new information about there, but there's still a lot to learn about all of them, but perhaps this one's the most mysterious. There's many ways of producing gravitational waves from phase transitions in the early universe. Probably the probably this star is the electric weak phase transition. And this can happen through many ways, through new scalars, affecting things at tree level or loop level. Multi-step phase transitions, vector-like fermions can also affect the electric phase transitions. But of course, beyond that, you can have dark sectors, you can have some guts with some symmetry breaking chain, or you can have some either QCD or dark QCD. So there's many motivations and many reasons to hope for some phase transition due to some physics beyond the standard model. Also, we have many detectors on the horizon. These are just the low frequency detectors, and there's just about everything featured. You have space-based interferometry, you have these ground-based detectors such as LIGO, and you also have the Einstein telescope. You have pulsar timing arrays down in the nanohertz, and in between you have Thea. And recently there's a proposal to also put space-based interferometers on the Lagrange points of the Earth's orbit. And that would give you also fill this region between Thea and Lisa. So there's, this is a huge focus of the next generation, which can cover everything a whole region of scales for where we might see a first order phase transition. So predicting a first order phase transition is if you're not going to use a simulation, you have a bit of a Rube Goldberg machine. So you start with a particular model, which is this Lagrangian. Then you want to describe well what your thermal evolution or effective potential is. And then you want to use that to derive some macroscopic thermal parameters, and then use that to derive some observable. And at the moment, the precision is very, very not great. However, that's fine, because before the LHC turned on, a few years before the LHC turns on, people who know the history of this tell me that next to linear order calculations were impossible. But now we're doing n cubed LO calculations. And similarly, a few years before the first experiments turn on, which can really test to see if there are phase transitions in the early universe, the theory errors are orders of magnitude, but hopefully by the time we either see something or don't see something, we can very, very much better understand it. And indeed, the theory errors are huge, even on the first step on this. Mark Harmash gave you a bit of a picture of how to go further along this Rube Goldberg machine. But this is a paper done a few years ago where we had a look at just the errors which come from doing standard calculations compared to a two-loop dimensional reduction calculation. And the standard calculation, you can look at this red line here. You're looking at 2 orders of magnitude error. And then, of course, if you go dimensional reduction, 2 loops, you're looking at this blue line, which is things get down to the percent level. Okay, so you might wonder why the errors are so bad in gravitational waves calculations. And you can kind of parameterize things by just looking at how the peak amplitude of the gravitational wave scale. So it scales roughly as this alpha, which is basically the change in the trace anomaly, or approximately the change in potential divided by temperature to the 4th power. And also this either mean bubble separation or your inverse timescale features as well. So if you just have a look at how these parameters scale just by simple dimensional analysis, you find that actually your gravitational wave has a peak amplitude as an 18th power sensitivity to your to uncertainties in your temperature. So to put things in perspective, if you get your temperature wrong by about 25%, then you might be 2 orders of magnitude off in your peak amplitude. And so the next part is, why is it challenging to get better than 25%, say, in your temperature? Is because perturbation theory at finite temperature starts to get a bit challenging. There's a couple of reasons for this. They're very related. They're basically due to the fact that at finite temperature, you don't just have couplings and couplings to worry about, or phase space suppression. Apologies for this pi, it should be the denominator on this left-hand side here. But you also have this mode occupation to worry about. And two issues with this. First, at high, when you do the high temperature expansion, you have this infrared divergence. This blows up and the mass goes to zero. Secondly, related is when you actually calculate these one loop integrals, we actually get some pi's in the numerator, and so the size of this this contribution here is actually only your phase space basically cancels. You just get something which is g squared t squared, which is the same as basically tree level size. And this is to be expected. This is why your tree level basically thermal corrections are basically as strong as your so your one loop thermal corrections are basically as strong as your tree level. And that's why it can change the shape of your tree level potential in the first place. But anyway, these mode occupations mix up your power counting and how large you expect a diagram to be just by looking at the loop order. And so to handle this, there's basically you have three different ways of organizing your perturbation theory. First, you have a standard way, which tries to deal with tries to delay the breakdown of perturbation theory essentially by resumming your mass diagrams. And so your mass obtains a thermal mass, and this thermal mass basically screens the long wave behavior, which becomes strongly coupled. And so then your mode occupation, if you expand it, it becomes T over square root of m squared plus this thermal mass. A second way of doing this is approach is, of course, dimensional reduction. What happens here is you notice that in imaginary time, that your time direction looks like a compactified direction of size 1 over t. And so then you can and so what that means is you're going to have, because you essentially have a 3D Kaluza-Klein theory with this compactified dimension, you can integrate out your Kaluza-Klein modes and write down a 3D effective theory. And what happens is you have this famous matching relationship on the bottom left-hand corner here, where you're essentially what's happening is your heavy modes screening your long-distance behavior. As a third method, which was discussed in the 90s, it kind of got I've only seen it applied in a realistic scenario within actually a dimensional reduction framework. I've also seen it used, similar methods used in QCD quite a bit. It kind of didn't get developed too much. There was one paper in 2015 which looked at this. But basically what it is instead of solving a gazillion diagrams at higher loop, what you do is you just do a numerical calculation instead of analytically solving all these diagrams. You solve this gap equation here, where you say the mass is equal to these one loop self-energy diagrams, which include the mass, which include the resum mass. So that pictorially, it looks like this first line here, but mathematically, it looks like this second line here. So it's the mass equals the bare mass plus basically the second derivative of your one loop potential evaluated with the full mass. And so this is a gap equation. You need to solve it numerically, but it includes a whole gazillion higher diagrams. And then a trick was discovered in the 90s where you wanted to avoid double counting of your super daisy diagrams. And so what you do is you actually put the resummed mass not into the full potential, but into the tadpole and integrate over the field. And then you add this any diagrams which are missing, which is basically the sunset. Okay, so to motivate why you might care about using a different method, well, obviously it's always nice to have different methods to double check the sanity of any result. But also, we eventually want to do scans of many, many models. And well, we have multiple methods at the moment. We have conventional methods, which are off by many orders of magnitude. This is really the Flintstone mobile in this analogy here. Lattice is fantastic, but you need to use the computing power of a small European country to analyze a few benchmarks in a model. Maybe things are more advanced than I appreciate, but that's the impression I get. Nextly, order dimensional reduction. Some of the processes being automated, particularly in the high temperature regime with Dr. Elgo. I recommend any new people in this field checking out that very valuable contribution by Philip Chico and others. You need to go to 2 loops to get improvement. That means calculating hundreds of diagrams. There's a lot of there's a bit of a learning gap if you're used to just conventional methods, and also you have to worry about when you go past the high temperature regime, you have to worry about when to use soft or ultra soft. So there's a few subtleties which you have to worry about. So it'd be nice to have like a bit of a Toyota Camry, something which is a bit better, which is better than the conventional methods, give you accurate results, but has less of a learning curve and is more convenient to use. And so I want to argue that it looks early days, but looks like we're developing basically a Toyota Camry for the field. So so basically, let's have a look at how this works and how to test drive and see how our cars work. And so the method which we discuss essentially in our paper, where we estimate the errors in conventional methods to be 2 orders of magnitude, is you have a look at basically the scale dependence of a particular model. And the reason why this is a sensible thing to do is if perturbation theory is working very well, then your implicit scale dependence, which comes from the running of your couplings, should cancel out your explicit scale dependence from this one loop Coleman-Weinberg pieces. Anything left over is from the higher order and gives you an idea of how big your 2 loop pieces are without actually explicitly calculating them. And so we can do this exercise with a single 5-4 theory. We have a look at the scale dependence of your tree level potential and the scale dependence of your Coleman-Weinberg potential. And lo and behold, as we add them together, the remaining piece is the 6th power in your coupling constant. However, when we go to finite temperature, we look at just, for example, the leading order correction is basically a quadratic term. And when we calculate the scale dependence of this term, there's nothing to cancel it out if we define our theory to 1 loop. And it's G 4th times phi squared T squared. And that's basically the same size as tree level pieces. And secondly, it's worth noting that things get worse when you have when phi is small compared to the temperature. So these these pieces are large, uncancelled, and so we expect that the scale dependence will be huge, which is indeed what we find. Okay, so now we're going to do something. A slightly jazzed up version of the standard methods. We're going to basically do Polanyi resummation. If you're familiar with standard methods, people either go Polanyi or Arnold Espinosa. But we'll go Polanyi basically because it's for reasons I won't go into here actually, but it allows for a more conservative comparison with improved methods. And what we do is what we're going to do to allow for comparison, since we have to add a diagram by hand to this tadpole method, we're going to add that same diagram by hand to this method too. And lo and behold, when we calculate the scale dependence, we find a residual piece, which goes as G squared T times this basically this M cubed term, this cubic term, over pi squared. So that's a piece which we're trying to beat if we're trying to basically improve on conventional methods. Dimensional reduction, you have something quite complicated. I didn't want to give, I've given a lot of equations in this talk, so I didn't want to overdo it. But basically the piece which we're trying to improve, it improves on standard methods, even with this 2-loop sunset included. And you essentially get this G 4th over pi cubed. So you get this big improvement. So there's that's where you get orders of magnitude improvement from the dimensional reduction at 2-loop. So most math on a slide for this talk. I apologize for this math, but these equations are fairly simple. Then the paper, it's I can also send out these slides, but it's fairly simple if we do the tadpole way. And I want to show basically just how close this is to the things people know. So this first equation here is the mass or the gap equation. This comes literally just from taking the second derivative of the one loop potential with thermal corrections. Now I've also put in, also done a high temperature expansion here for convenience, but you don't have to do that when doing a numerical calculation. The second line here is the tadpole equation, which we're going to integrate over the field. And this is just the first derivative of the one loop potential. So this is, if you know how to calculate one loop potentials, you know how to do this. So there's very, very little learning curve, which is something which we hope will eventually be attractive. So then if we calculate the scale dependence of the tadpole and the gap equation, we can see the effect of how it's including many higher orders in this. So you see the gap, the tadpole term, which is the third equation here, has this term here which is mu dm squared d mu. And if you have a look at the we can sub in this dm squared d mu squared, which is the next line. And you see that also has this mu dm squared d mu, but you also get this additional power of g squared over 8 pi. So by iteratively using the gap equation, you get higher and higher powers of g squared over pi, and this term eventually vanishes. It disappears. And so this is this cancels many higher order terms, which is a very nice feature. The overall scale dependence, so you have a choice whether you're lazy or not. But parametrically, you always get something which is g to the power 4th over pi cubed. But you can also put the sunset in the gap equation, in which case you get the first term cancelling and you just get the final term. If not, you also get the first term here. But it's parametrically the same size as dimensional reduction. So that's very, very exciting. We also, the one field case you can't really have gravitational waves from, it's you can't get a barrier from. But two field case you can, we won't go through the calculation, but this is also something you can do analytically as well as numerically. And once again, we find parametrically that your standard approach gives you this g squared. Dimensional reduction and OPD give you basically the same scaling. But the advantage of OPD is it's again trivial to go beyond the high temperature expansion. Now it's not terrible to do it in dimensional reduction to go beyond high temperature expansion. Of course, you have to use if you're using DR Algo, version 1 doesn't have that capability, but yeah, you are going to have to do in your matching relations. You are going to have to use your full integrals, and yeah, so that's additional layer of pain. Okay, so then in terms of numerical results, things were not as clean cut as the analytic results. So and the reason is just because you get a strong phase first order phase transition, that your coupling constants just have to be absolutely massive, and so even zero temperature perturbativity is not great. But in any case, this is what we get. But one thing I thought which was quite interesting about this is, yes, we get quite a bit of scale dependence as we expect in these models. But what I thought was quite interesting about this, and a side point beyond like comparing different methods and different ways of recent summing, is that the maximum gravitational wave amplitude you can actually produce in this model is orders of magnitude different if you do a more careful calculation than if you do the standard calculation. And so that's telling us that even if you want to know global features of a model and do a scan, that conventional methods aren't cutting it. Actually, they're not telling us the truth about like exactly what the blob of parameter space is looking for. If you want to know questions like, what is the largest gravitational wave amplitude I can produce in the model? Okay, so in conclusion, so we need to greatly improve the accuracy of gravitational wave calculations, and we're right at the right time to do that, because some big experiments are about to launch. This is very hard to do, You know, we have this fantastic methods of simulations and dimensional reduction, and OPD or this tadpole method provides a method very close to what people know. So there's a very small learning curve. It's quite easy to use, and it seems to have very similar accuracy to dimensional reduction, and also it's trivial to extend to when the high temperature breaks down. You don't have to have any of the sort of checks or subtleties, as far as I can tell. We need to develop this technology more for more complicated models. So we can't say anything conclusive yet, but they're saying there's no such thing as a free lunch, where we're hoping that this tadpole method is a bit of a free lunch for the field. But early days, but lots of promise. Thank you.
All right, thank you, Graham, for this very nice talk. We have time for questions. Please unmute and ask.
Could you go back to the previous slide?
Yes.
Maybe I missed something, but what is the model again? Because if this is the maximal amplitude, it's not a particularly strong transition.
It's just 254 theory, so you don't expect it to be a very strong transition. It's not a great model if you're looking for gravitational waves, because there's only 1 degree of freedom getting heavy. Yeah, so
right.
Not going to be
well,
very
but
good.
with an amplitude this small, well,
Yeah.
something's telling me.
This is not real phenomenology. I mean, when we do more complicated models, the reason for choosing this is because we wanted to. There were some subtleties in when you add gauge fields, and so we wanted to basically separate the two projects and into two. So yeah, we'll have like much stronger models when we have like say SU2 being broken or something.
Right. Okay. Well, I mean, usually if a gravitational wave signal is this weak, then probably if you did something on the lattice directly, you wouldn't even find a first order transition to begin with.
Yeah. Yeah, well, that's one thing which is super interesting about this gap method, is it does actually seem to tell the difference between when like it was used for finding a first order transit, for finding the critical endpoint for when the Higgs mass is too heavy. It got the wrong answer, but it is something which actually does work, unlike perturbation theory. And similar in QCD, gap methods also do find a critical endpoint. In fact, I think it's the only method which can find a critical endpoint. It's actually, if the gap method is saying there's still a first order transition, well, that's not true because it gives the wrong critical endpoint compared to lattice, but it is at least gives a critical endpoint.
Right. Well, I can have another question if no one else wants to.
I'll go for it, yeah.
So the other one is, so you mentioned that the error that we get is like 2 orders of magnitude, just based on, say, getting the temperature a little bit wrong. But, well, I always worry about the interpretation of this, because it's not really just that you use a different method on the same, because the connection that we want to make is from the fundamental model in particle physics to the gravitational wave signal. And you're using the in-between parameters and then checking how the error on those converts to gravitational waves. But in practice, wouldn't changing one of the couplings in your model by 1% give you the same sort of change in the gravitational wave spectrum?
Yes, that's a good question. So that's something which we don't know the full extent of how much this affects global features of the model compared to just a fine-tuned response to exactly where in the parameter space. However, it looks like because my screen froze, I was going to go to that last plot again, because the maximal amplitude you can get in a model seems to vary by orders of magnitude depending on the accuracy. That seems to be strong evidence that actually it is actually global features. There's been my understanding is Ollie Gould is actually looking at this to look at basically the blobs of alpha and beta over H, like those blobs of parameter space you get, say, for different scales. So you take compared to what you get in next to dimensional reduction. And so he's mentioned a couple of times you get different blobs. So it looks like you change full global features of your model as well. I think like the first model we looked at, it's because you have one parameter in your model, it's because it's SMEFT, you just have your cutoff. I mean, it's a fake model, but who cares? Then I mean, you can always get stronger and stronger as you go up there. Of course, whether you can always, even then, I don't think you get the same blob in the alpha versus beta over H claim, for example, but I haven't done that calculation myself.
Okay, well, I would think that if the blob changes, then the values of parameters that are allowed also change. And so the maximal value, I would expect to be similar at least.
Yeah, so it seems that, it seems you get an asymptote. So the gravitational wave grows stronger. We didn't go all the way to perturbativity limit. We went half the perturbativity limit, because then who's going to trust anything if you get that high? But you kind of, the gravitational wave seems to asymptote roughly as you get your coupling gets larger and larger. Polar coupling gets larger and larger. So it seems that you do reach this maximum.
Well, I mean, that's always the case because eventually I guess you're trying to supercool the transition such that the minima are actually getting degenerate slowly. I think this is usually the bound. But I think if your calculation changes the potential, you'll just hit that at different points and you'll reach the same, let's say, result approximately.
Yeah, it looks like you don't. You get like differences in your latent heat and how quickly, and your beta over H. Yeah, it looks like where the asymptote is different for the two methods. I know that so I've been tempted to do this for a while, but no, that's something which Ollie Gould has talked about during something he's been working on for a while, is basically just demonstrating that you get these global differences. And also, if you do get differences in the blob, it's not just the peak amplitude which matters. I think like Mark Hindmarsh's paper with Chloe Gowling says, in principle, we can construct 4, perhaps 3. I know Urinde had a paper looking at a more conservative approach. 3 or 4 thermal parameters from the spectrum that we see. So that blob does matter, especially if we want to say, okay, what model do we have that's producing this gravitational wave? Once you have 3 or 4 parameters to fix, that gives you, quite a bit of information about what your physics is.
Well, okay, we're running out of time, so maybe let's.
Yeah. Okay. Thanks. Okay. So yeah, thanks, Graham. And over to the organizers for any announcement. So we have a break now. Thank you.
Indeed, we have a break now. That's done. So it would be nice to see this in some other model that the amplitude is actually strong.
Yeah, this model was chosen mostly for the analytic work because we need to sort out a bunch of stuff, and the other reason for separating our gauge bosons is you can in principle write a gap equation for the gauge bosons as well, and it's not clear whether we need that, and that ended up being complicated enough that it's worth its own paper essentially, especially since postdoc is on the market, and we wanted to get this out. Sorry, it's a PhD, but he's on the market.
Yeah, I know this is not trivial. No, we are actually trying to also somehow check in some models with Philip Chico, actually.
Okay. Similar calculation where you're looking at like the blobs, or?
Yeah, pretty much. Just check the global features, I guess.
Yeah, I've only heard anecdotes of what people have done. I've never seen it in print, so it'll be very interesting to see like whether the full blobs change or whether you have fine-tuned response to the parameters. It seems, at least for this model, you get a global feature change.
Well, I mean, I'm sure the blobs will change, but I don't think this would change the, say, range of results you could get. That's what surprises me.
Mm-hmm. Yeah, like I guess, are you comparing like a full one, comparing one loop to 2 loop, or one loop at a particular scale to one loop at different scale compared to the full 2 loop or something.
Yeah. That's true. Yeah, but I was always under the impression that, the blob changes, but in practice, you just meaning that you can get your interpretation of the model parameters wrong, but not really, change the results that you can get.
Yeah, I think if the blob changes, that's still quite interesting.
Yes, but then it depends how much, right? Because if the error that you're making is like 1%.
If it's just like the blob's just moving around, it's like a mapping onto itself through this scale dependence, then it's obviously less interesting if it's like completely warping. If you calculate it, say like t over t scale versus 2 pi t.
Right. Well, yeah, it's not completely obvious at the moment. You're right.
Do you have preliminary results out of curiosity?
Well, not yet, because we're trying to use Drago, so it's it's a bit involved.
Yeah, I don't know if there's been a scan done in dimension reduction, so that my understanding is that would be the first, if you're planning to do that.
Well,
even a simpler calculation would be easy. Just use standard Arnold-Espinosa and just use 2 RG scales and just see what the blob looks like in each case, and just show that you have like a big change one way or another. For a simple model, say like dark SU2 or dark SU1.
sure. Yeah, that would be. Oh, we're trying to go beyond that. It's true that, although that would be also inconclusive, because then you just, right, if you don't include the, say, better calculation, and there's no implication which of those makes more sense than the other. You can only estimate the error. Yeah, actually,
it's still
makes
well,
sense.
telling you that you need to do the 2 loop, which is the whole point of checking in the first place, right? To know which one of those is right. I mean, of course, it's not the cherry on top would be, of course, to put in the 2 loop.
Yeah, so with changing the scale with the standard techniques, that's what we have recently done. And the change in the results is actually huge for a model with strong supercooling, like conformal model.
Did you have a look at the blobs? Or just single?
Yeah, well, like we made a full scan of the parameter space at different scales, and it changes radically.
Great.
Yeah, so, well, and in those conformal models, the scales that are involved are very different, right? So like different scale at which you tunnel, different scale at which you have a minimum. So you can really go through different energy scales, and you do see the difference.
Right.
That's good. Yeah. Do you also see a scale change in the maximum amplitude in that model?
Yes. Well, like we didn't really look at the maximum amplitude, but for example, what you see is that if you do the analysis with RG improvement, you can have bubble collisions. And if you do it at fixed scale, you don't have bubble collisions as source of gravitational waves. So it really not only changes, the numbers, but also the qualitative results.
Well, right, but in this model, because you changed from the mu scale being mz or being the mass of the new particle, which can be 10 to the power 7 GeV, right?
Yes, but you see that no, but you also compare to RG improved version, and in that RG improved version, you do have bubble collisions, and if you do fixed scale, and no matter whether it's mz or the mass of the new particle, you don't have bubble collisions in that case.
Oh, okay.
Yeah, and actually, mz is much closer to the scale at which you tunnel, whereas the mass of this new particle is much closer to the scale of your minimum. So it's, well, hard to decide which fixed scale would be better.
That's
Yeah,
true.
and,
But at least in your model, I can safely predict that the maximal amplitude doesn't change because it's always huge, because alpha is like 10 to the power 10, right?
Yeah, and alpha actually, doesn't really matter anymore because it's so huge that it cancels out in the formulas.
Yeah. So, see, the maximum doesn't change.
Well, but the allowed parameter space does change. Because, for example, you don't percolate in some part, and that the shape of this region depends on the scale. And the region where you go to QCD, source space transition, depends on how you fix the scale.
That's cool.
True,
When's the paper coming out?
It's out
It's
already.
an archive. Yeah.
Oh, fantastic. What's the archive number? Just look it up.
Yeah, I don't remember the number.
I have the number. I'm looking at it now. Just to remember.
Can look for.
Yeah, but I would say that this is a special case in the sense that because the dependence on the masses is logarithmic for a lot of things. So it's sort of the variation you expect to be bigger than usual in a sense of the allowed parameter space. And maybe it's also a special case in the sense that it's easier to get the potential more wrong because of this running. Because running is what makes the shape of the potential to begin with. While
that's true. That's true. Yeah.
Well,
it's important because there is no one scale that would be correct for your computations. So the necessity of running is somehow inherent to the model. That is true. If you have a model where everything happens around 100 GeV, then you would expect that this running doesn't matter that much.
So if you have a thermally induced barrier, you've usually got a huge coupling. So then the model running matters a lot. Alternatively, if you have a really, really small quarter coupling, which can also give you a strong, essentially you have a hierarchy of two masses. You always need to have a large hierarchy of two masses to get a strong phase transition. And yeah, you always, for example, you gauge boson over your Higgs. And that's always the case where running is going to matter a lot.
Yes.
Exactly. Yes, but here it's probably a little different because of this scale invariance, but
yeah.
Right. Well, we'll see. There's progress to be made for sure.
There is.
Okay, so maybe let's go because we have 15 more minutes of the break. But
so let's take a break and see you in a quarter, hopefully. Thanks for the talk. Oh, by the way, I wanted to ask you because those methods of solving the gap equation, that's an old method, right?
Yeah, it's quite.
So what you do, you apply this method and basically formulate new conclusions out of it. But the method itself is as it used to be, right? You haven't modified it.
Yeah. So there's so including the tadpole stuff that was all in the 90s. So basically, we're just trying to show that it works analytically and finding out what happens numerically, and then trying to basically produce technology for people to use. We unfortunately we didn't invent the gap method.
Sorry, can you say again?
Unfortunately, we didn't invent the gap method.
No, I was wondering whether you modified it to any extent.
No. I guess we didn't modify it, but I guess the only modification worth mentioning was also done in the 90s to plug it into the tadpole rather than the full.
Okay, thanks.
Yes.
Okay, see you in a bit then.
See you soon. How do I stop sharing?
Hi, Joachim.
Hi.
I think you're the chair, right? So yeah, I made you a co-host.
That's what I heard. Yes.
Oh, okay. Yeah. Well, just in case, I made you a co-host. And
okay, thank you.
Yeah, no difference basically. Anybody can share screen anyway. So,
yeah.
Okay.
Hello. I'll start sharing my screen then, right?
Oh yeah.
Yeah. Maybe you can do that already. That would be wonderful. Yeah.
Does it work?
Perfect.
It's working. So when you start and I start recording, right?
Yeah.
Okay.
I think it's 1 more minute. Let's try to be more or less on time. And
yeah.
So Marike, the time allocated for the talk is 20 minutes as far as I can see. So what I would probably do that up when you're 20 minutes in, I'll give you some sort of hints. So then you know that you still have 10 minutes left, including discussion. Would that work or?
Yeah, that's fine. You can just speak up, I guess. Right.
Yeah.
That's probably the easiest way to get my attention.
Okay, I'll do that. Okay, then I think we should slowly get restarted. So if right, so welcome back to the second session of the day. We now have 2 talks planned plus the panel discussion. And I'd say we start right away with Marike Postma and the electric phase transition. Is effective field theory just a toy?
Yes,
take it away,
thank you and welcome everyone. Yeah, I will talk about whether an effective field theory description for the electric phase transition is a good idea. And this is sort of based on earlier work where we actually looked at baryogenesis, electric baryogenesis, together with Graham, so the previous speaker, and with Jody de Vries and Jorinde van der Vis. And then later together with Graham, we looked at a more systematic approach and just looking at the phase transition itself. So given the previous talk, I don't think I have to give too much introduction, but just let me point out the notation that I will use the phi field for the Higgs doublet, and then for the classical field value that gets the expectation value, we'll use the letter H. So this is the Higgs potential at 0 temperature, as you've seen. Oh, sorry. In the previous talks, at finite temperature, you get corrections and you have a phase transition in the early universe, which can be either second order or first order, depending on the particle content of your theory. And in particular, to get a first order phase transition, which is what you want to get an observable gravitational wave signal, you need new physics. So just before going into the details of it, let me just point out that there's still some room for new physics, because what we have measured about the Higgs potential so far is the location of the minimum. So the FEV, which is 246 GeV, and then the Higgs mass, which gives you the curvature around the minimum. So basically, if you do a Taylor expansion around the minimum, you get the first 2 terms of the expansion. But if you want to probe the Higgs potential in more detail, you have to go to higher order, and you want, for example, to measure the triple Higgs coupling. And in practice, this is really hard because just the rate of events in the LHC is very, very small. And at the moment, as you can see here on the left, if you look at the coupling, the measured coupling divided by what it should be in the standard model, it's at the moment bounded between -1 and 7. So there's quite a large room for some deviation from the standard Higgs model potential. And for example, both of the lines, the 2 potentials shown here, they're both perfectly fine with the data. So there is still room for new physics. So let me then come to the topic of my talk. Can we describe this new physics that's needed for a first order phase transition using effective field theory methods? let me first review sort of the idea of the EFT is that so to describe a process at a given scale, you only need to include the degrees of freedom that are actually important at that scale, and all physics at a higher scale, so at shorter distances, you can integrate out, or you can think of it, you can average over this. And in the current setup, the scale of the process is the electroweak scale, so around 100 GeV, which is the temperature at the electroweak phase transition. And the new physics has to be above this scale because we haven't seen it yet at the LHC. So if it's heavy enough, we can integrate it out. And the effects of the heavy physics you can then incorporate in, as it's sort of reflected in new interactions between the light degrees of freedom, in our case, the standard model degrees of freedom. And the Lagrangian you end up with is the following. So you get the usual standard model piece plus a whole tower of higher order interactions that incorporate the effects of the heavy physics that you have integrated out. So here are the higher dimensional operators consisting of the light degrees, so the standard model fields. Lambda is the cutoff scale, and you can think of it as the mass of the heavy physics, so the heavy particles you've integrated out, the dimension, and Ci here is the Wilson coefficients that gives the strength of each of these interactions. And given a certain UV model, say you consider standard model plus extra Higgs doublets, you can actually, if you know your UV physics, you can calculate these Wilson coefficients. So why is it useful to go to this effective Lagrangian description? Well, first of all, it's relatively simple. You reduce the number of degrees of freedom because you got rid of the heavy ones. And for example, for the case I'm interested in, where you look at the Higgs potential, if you forget about the loop corrections and the thermal corrections, then it's just the potential that you now end up with of just a single Higgs field and no extra degrees of freedom. So that's nice. Secondly, it provides you a model-independent way of describing all possible new physics models, because you can just include all type of operators here that are allowed by symmetries. And this covers the whole range of UV models. And then you can treat them in one unified approach without making choices about what you think the UV should be. And secondly, it is a systematic expansion. And what I mean by this is that in principle, you have a whole tower, an infinite tower of higher dimensional operators. But as you can see, if you go to higher dimensions, the operators are suppressed by a larger power of this cutoff scale. And if your energy of your process is below this cutoff scale, which is sort of the assumptions, then higher and higher order operators are more and more suppressed. So given that you want to calculate say the electroweak phase transition at a given precision, you can then truncate your infinite tower and keep only the first order terms in this tower needed for the precision that you want. But of course, all this works is if you have a separation of scales between the electroweak phase transition, the electroweak scale, and the new physics. So sort of this is the question I will be addressing in the rest of my talk. Is the EFT description actually valid for the electroweak scale transition, phase transition? And the question here really is there enough separation of scales between the standard model degrees of freedom and your new physics? And sort of to address this question, I will first discuss how the phase transition actually looks in the standard model effective theory. So the setup that I just discussed. And then later I will go to effective UV completions and see whether you actually can get the EFT description. So let's first look at the phase transition dynamics in the effective field theory, so in the standard model effective field theory. And I'm So I'm just working here at the level of that the theory includes all the standard model particles as the light degrees of freedom. And we saw in Graham's talk before, and it was also mentioned earlier, that you might also go one step further and integrate out part of the standard model modes as well to go to the dimensional reduced theory and to get a proper description of the finite temperature effects. This you can still do, but then what I'm discussing today here is just the first step in this program. Can you do this in a two-step way, and where the middle step is really truly model independent, or do you have to do this step in a one-step transition and separately? So you have to do that separately for every single UV completion or not? Anyway, so let me continue and discuss the standard model effective field theory. Like I said, I'm interested in the dynamics of the Higgs field. So I've here listed the operators involving the Higgs field. And because of gauge symmetry, you only get operators with an even dimension. So the first three terms are here the usual standard model terms. So you have the kinetic term for the Higgs field, the mass term, and the quartic interaction. And then at dimension 6, you get 3 extra operators that you can write down given the symmetries that you have in the standard model. And the first 2 here are corrections to the kinetic terms, and then here a correction to the potential. And then you can go on, and I've given you one of the operators you get at dimension 8. As it turned out, these first 2 corrections to the kinetic terms, they're actually subdominant if you want to describe the dynamics of the phase transition. So for simplicity, I will neglect them during this talk. In our paper, we actually included their effects, but just to keep the presentation simple. So then the corrections we're looking at is the dimension 6, and to check the validity of the EFT, I'm also interested in the dimension 8 term. So what you now can do to get it in a more easily understandable form to see what's going on is that you rewrite this potential in observable quantities. So the Higgs mass, which we have measured, and the Higgs VEV that we have measured. So you can, by solving, you can substitute these 2 parameters, mu and lambda, for the observables. And if you do that, you can write the Higgs potential in the following way, where I remind you, H is the classical field direction that gets a VEV. So this is the Higgs potential at 0 temperature. If you want to look at the phase transition and you want to do precision, you do get correction to it as well. And I've written here down the sort of the one loop corrections, quantum corrections, and the thermal corrections. But these are both perturbative corrections. So as long as we're in the perturbative regimes, they are relatively small. But you can see if you want in this potential to have a first or the phase transition, you need a minimum at the origin and a minimum at finite field value, but with a barrier in between. So sort of what you want is that at the origin, the mass term dominates. So that gives you it has a positive mass term, gives you this positive curvature here. Then at some point you want the negative quartic term to kick in to get this maximum here, and then that the slope of the potential is negative. And then at larger field value, the dimension 6 term should become the dominant term. So you get this minimum here. And so if we now look at this potential here, you see that depending on the, it's actually scale of the new physics. So I should have mentioned it maybe before, but if you look, I've parameterized the dimension 6 operator by the cutoff scale lambda. And then the relative strength of the dimension 8 is parameterized by this C8 term. And you see that to get depending on the scale of this lambda, so how large this dimension 6 term is, you can switch the sign of both the quadratic and the quartic term. And to get this first order phase transition, you want to be close to this sign switch, because then together with the smallish perturbative corrections, you can actually get this form of the potential and have a first order phase transition. So if your lambda is way too large and this term is too small, then you need way too large and non-perturbative corrections, and you don't have a first order phase transition. On the other hand, if lambda is very small, then actually the mass term becomes large and the minimum here at the origin becomes very deep. And then you run into the trouble that the phase transition might never happen, as you're stuck in the false vacuum forever, or at least for a longer time than the age of the universe. So this then gives the estimate to get a first order phase transition. You have to have the lambda close to where these two terms switch sign. And that's sort of the estimate that I've written here at the right upper half of the slide, that the cutoff scale should be of this parametric form. And if you plug in the measured value, this gives you a scale of cutoff between 700 and 1000 GeV approximately. And secondly, as I mentioned, for the EFT to be valid, you want to be able to truncate this higher order of operators. So you have dimension 6, 8, 10, 12, etc. And so the higher order should become smaller and smaller. And what we have checked is that for this to that the dimension 8 should be actually smaller than the dimension 6 term. And this gives you this second constraints. And this is sort of where you say that this term in the zero temperature minimum should be half, at least smaller than half times this term, because otherwise the series wouldn't converge. So this is all sort of estimates. We have also checked this by actually doing a numerical scan of the parameter space and seeing where you actually get a first order phase transition. So this plot over here shows the strength of the C8 coupling the dimension 8 versus lambda, and blue gives you the colored region. You have a first order phase transition, and the strength of the phase transition given by V over T gives you is the color coding here. And you see indeed that our estimate is pretty good, in the sense that 700 to 100 GeV is indeed the region where you get a strong first order phase transition. The other important thing is that if you neglect the dimension 8 coupling, you're along this red line. But then if you turn it on, you see that the strength of the phase transition actually changes. So if you want to calculate the sort of parameters of your transition precisely, you want this C8 coupling, actually it should be the absolute value to be smaller than 1. So then you get an approximate 5 to 10% precision. And this constraint is actually stronger than the separation of scales. So you might have a separation of scales and you'll be able to truncate your theory, but for precision, you still may want to include the dimension 8 term. So in the last part, let me then look at explicit UV completions and see whether what it implies, what these UV completions imply for the EFT that they give. So for simplicity, just look at a new scalar degree of freedom. You can look at other setups with vector degrees, etc., but they give the undimensional crowd similar results. So we have the standard model plus an extra singlet field in this case, which is denoted by S here. And then you may have a linear term in S with a coupling A to the X field. And then you have a quadratic term in the singlet and higher order terms, so cubic, quartic, etc. So this is the kinetic term mass for the singlet, and this is the coupling to the X field. And so the what you get, the pheno depends whether these linear terms exist or not. And let's first look at the case where you have a set-2 symmetry. So the Lagrangian is invariant under S going to minus S, and this kills off this linear term, and you only have the quadratic term. Then you can see in the UV theorem, in the UV theory, you can build diagrams like this with an S in the loop and then 6 Higgs lags. So this would give you an interaction that involves 6 Higgs fields. And then in the low energy limit, that your energy is lower than the mass of the scalar running in the loop. This gives rise to an effective coupling in the EFT and dimension 6 coupling. So this is what integrating out means in terms of Feynman diagrams. So you can do this systematically, also looking at diagrams with more lags of the Higgs fields, and that's written down here. And so this gives you the U is this coupling here to the Higgs field. This gives you the dimension 6 term, the dimension 8, etc. And CS is here the degrees of freedom. So in this case, for complex scalar, it would be 2. For real scalar, it would be 1. For more complicated multiplets, you get a different number. Anyway, you can now match this to the sort of EFT dimension 6 and dimension 8 operators that I introduced before. And so you can actually read off what lambda and C8 is in terms of the parameters of this theory, which is kappa, the coupling to the Higgs, and the mass m of the scalar singlet. And then we use our estimate, when do you get a first order phase transition, because we got a constraint on the size of lambda for this. And this constraints I've written down here again, but now translated in the parameters of your UV theory. And so you need that this combination should be equal in the Higgs case to about 0.5. Well, is that possible? It turns out it is not, because first of all, this first factor, you want to be much smaller than 1, because this is kappa here is the coupling of your UV theory. And if it's much large, if this combination is much larger than 1, then it means that your UV theory is actually non-perturbative. So basically that you cannot calculate anything anymore, at least not in a perturbative way, because you cannot stop at 1 loop or 2 loop, but you have to include all loop corrections. And to be able to actually calculate something, we stick to perturbative theories here. And secondly, if you want the dimension 8 term to be smaller than the dimension 6 terms, so you want your EFT approach to be valid, and you want to have a separation of scales, then this term should be smaller than 1. Well, both smaller than 1, you cannot get 0.5 here. So in these kind of setups where you have loop level matching, so the diagrams here are loop level diagrams, you cannot if you go to the EFT language, this cannot describe the UV theory at all. So let's then look at the other case where you also have this linear term in the singlet. So we don't have a set-2 symmetry anymore for the scalar, and we allow for this field.
Marike, you have about 10 minutes left, including discussion.
Ah, that's more than enough. Thanks. So if you look at the equations of motion here, you see that the scalar field now actually obtains a VEV. So, and this means that you get mixing between the Higgs and the singlet, and you have strong constraints from electroweak precision on this. And basically the only allowed extensions of the UV extensions, and that can give you something for the electroweak phase transitions are then a singlet or a doublet with the same quantum numbers as the Higgs field. The doublet doesn't work because it gives the wrong sign for your dimension 6 term, so we left with the singlet. So for the singlet, we do the same thing again. Now we can construct a dimension 6 diagram and integrate it out in the low energy limit, where this diagram is 3 level. And you get similar results now. And if you require, again, first order phase transition, now you get a little bit better results, because before basically, because this is a 3-level diagram and not a loop level diagram, you win for this factor. So this factor, you want to be smaller than 4 pi. And so A here is the coupling. So compared to your loop level, you gain this factor 4 pi here. And this allows you to actually satisfy this constraint, although it's still a bit marginal. And so this is the last slide. Because it's marginally, we once again did the numerical scan. And so this is the results for the UV theory, the parameters M and the FEF of the extra scalar. And this is which you can map then to the C8 and lambda in the EFT. And red lines are mapped from here to here. And the important, I just want to point out 2 things: that you have to be above this green line to be in the region where the EFT description is valid. So only part of parameter space of the full UV theory maps to the EFT. And you can also turn it around, because if you look at these red lines and where they lie here, then in the EFT, there's much more parameter space that's never reached actually by your UV theory. So the conclusion is that, well, the standard model vector field theory actually is not a very useful thing to use for the electroweak phase transition, because there's at most one theory, namely the singlet extension, that can give you part of the parameter space in your EFT. But if it's only one, there is actually no use of using the EFT description. You might as well use the scalar description. And the problem is actually that you need very large corrections to the Higgs potential to get a first order phase transition. And because you need these large corrections, you don't have the separation of scales, because even though this cutoff is fairly large, you're comparing this to the dimension 4 term, for example, where this lambda is 0.1 instead of 1. So this is still a large correction. And as the final remarks, and then I'll stop, the results can be generalized to dark sector phase transition as well. Thank you.
Okay, thank you
Sorry,
very
I
much.
went a little bit over time.
No, not at all, not at all. Thanks a lot for this highly interesting talk and the interesting conclusion. Do we have questions? If you have a question, just raise your hand or unmute yourself. Okay, then maybe I start. So this smells very much like a no-lose theorem, a no-go theorem you derive, right? That higher order corrections almost never can really lead to a first order phase transition. You need all the physics responsible for the phase transition to be roughly at the same scale, right?
Exactly. Yeah, that's yes, that's basically it. But it's not. There's still some assumptions that went in our derivation, but still the physics that you describe is there. So I've even though these assumptions are there, it's hard, I think, to actually get around them. But the assumptions are that we're using is that the UV is perturbative. So if you go to strong strong sectors, things might be a little bit different. And the second thing is that we sort of look at setups where the extra degrees of freedom are just 1 or 2. In principle, you can go to large n limits. You have to still do something special, because if you increase n, your constraints are perturbative, so you get a larger corrections to the exponential, which is great, but also your constraints on perturbativity become stronger. So you have to sort of make this theory in a way that they don't scale in the same way, otherwise you don't gain anything. But that would be maybe one way around this. But then even if you can construct it, you might as well just, I mean, the EFT approach doesn't really make sense anymore as a sort of model independent way of doing things.
Yeah, I could imagine that when you go to dark sectors and you allow yourself complete freedom in how you set up your low energy degrees of freedom in the dark sector, then maybe with some tuning you can construct a situation where the low energy part of the Lagrangian is just barely short of generating a first order phase transition, and then even a small correction maybe pushes you above the threshold for it. But
yes, exactly. The problem is that in the standard model, the X mass is measured. If you could tune to the 65, if you added freedom, then you can raise lambda scale and everything is fine. We just included some discussion of that in the paper, because there are often also people, well, with the gravitational wave often look at dark sectors, and it's just something that you have to check, that whether it actually makes sense that you're in the parameter space where you're closer to the standard model setup, or the situation that you're describing where everything is actually fine.
Yeah.
Because even, yeah, like in this case, the scale of the cutoff seems to be, well, 1000 GeV. It's not that much above the electroweak phase transition, but you might think, okay, it's still quite above, but yeah, that can be sometimes misleading.
Yeah. Okay, thank you. Do we have additional questions to Marieke? I don't see any hands up, and since we're anyway going to have the discussion session in half an hour, I propose that we move on to the next talk. So thank you again, Marieke, for the very interesting talk. Our next speaker is Bibhushan, who I see already online. Yeah, Bibhushan Shakya, who is going to tell us about gravitational waves from feebly interacting particles in a first order phase transition.
Indeed, and you can see me, and I trust that you can see my screen.
Yeah, it's now full screen, so the floor is yours.
Perfect. Thank you, Joachim. Hi, everyone. Good morning, good afternoon, good evening, depending on where you are. Thanks for staying with us, right? And I've been tasked with ending this day of exciting talks of physics related to gravitational waves and phase transitions. So the talk I will give you today is based on this paper that we finished earlier this month. This is a paper in collaboration with Rusike Gino and Joranda van de Vis, who were both postdocs at DAISY when we started on this path, but now have moved on to other institutions. So the benefit of being the final speaker of the day is that I don't need to give you an introduction to all the physics that is exciting or relevant, right? We're all experts on this already, so I can jump right in. And so the most interesting question and the most important question to ask in terms of figuring out what the gravitational wave signals of a phase transition are is the question of where does the energy released in the phase transition go? And if you look at the literature, there seem to be one of two ways that this can go in. Either all of the energy is stored in the walls of the bubbles, and as the bubbles expand, there's no way to dissipate the energy, so the walls just keep picking up energy, they keep accelerating, they grow more and more energetic. That's one possibility. Otherwise, if there's an efficient way of dissipating this energy into the plasma, if there are significant interactions with the plasma, then it ends up that most of the energy is going towards generating bulk fluid motion in the plasma, where you generate sound waves and turbulence, and this is where now most of your energy lives in. And so both of these configurations are very extensively studied, and we now know that they are both great sources of producing gravitational waves, and these gravitational waves have very distinct features depending on the details of how these things are generated and how they interact, right? And so the question that we wanted to look at instead was, do these two options sort of exhaust all the possibilities, or are there other possibilities for where the energy can go? And in particular, what we wanted to look at in more detail was whether you could be in a situation where all of the energy goes into particles. And when I say particles, of course, the sound waves and turbulence is also coming from configurations where the energy goes into particles. It's just that these particles now have some collective behavior as a fluid. And so you have a fluid description of these setups. What we were interested in, our question was the opposite regime, where you cannot have a collective description of the setup because these particles are so weakly interacting that they don't interact with each other at all. And you really have to think about them as individual degrees of freedom that just free stream on their own and don't interact with anything else. So the question we wanted to ask was, is this something that can occur in realistic frameworks of first order phase transitions? If this happens, then do these configurations still generate gravitational waves? Are these gravitational waves different from the other gravitational waves we know from the more familiar sources? And most important of all, are these gravitational waves observable? And when we started on this, we were actually worried that this might be a sort of a blind spot for gravitational waves, where even though you have a very strong phase transition in some sector, you might end up in configurations that are not useful for generating gravitational waves, and you might not see any signals at all. But fortunately, the answers turned out to be what we had hoped for. And so the answers to all of these questions turn out to be yes, 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 and yes. And so I will tell you the story of how this thing unfolds. So to sort of look at where how you can transfer energy from the phase transition into particles. And this is something that Michael talked about earlier in his talk, so I won't go into a lot of detail. But the idea is that an efficient way of transferring energy to particles is if these particles gain mass from the phase transition. So imagine there is a thermal population of some particle X sitting in the universe. In the symmetric phase, when these bubbles nucleate and expand, they have to enter these bubbles and go into the broken phase. And in the broken phase, they're massive. And because they're massive, then there's some sort of energy conservation condition that tells you whether they can enter the bubble or not. And the most straightforward way to see it is in the rest of the bubble wall, where if these particles come in with a lot of energy, then they can penetrate and enter and convert their energy into mass. But if they don't have enough energy, then they just get reflected back to the symmetric phase. And every time a particle enters, there is some momentum transfer between the wall and the particle, which is sort of mass squared over energy. And you can calculate what the energy cost of having a full thermal ensemble of these particles crossing into the bubbles is. That energy is roughly 1/24 m²t². This is the famous Bodecker and Moore formula that we'll all learn in kindergarten, right? And so there's a pressure, or this energy cost of entering particles that become massive into the bubbles. And if this energy sort of saturates all of the energy that you release in the phase transition, then you have a configuration where all of the energy that is released in the phase transition goes into these particles. And as a consequence of that, the wall stops accelerating. It just reaches some terminal velocity. And this is something that can happen with certain parameters. And in particular, the condition for this to be satisfied is given by this formula, where the mass over the temperature of the phase transition has to be bigger than, let's say, some order one number. So what we did was we looked at some scenarios like this. We looked at configurations where the mass over temperature was some order one number. And we looked at configurations where most of these particles entered the bubble so that the reflected fraction was actually very negligible and you could just ignore it for the purpose of simplicity. The opposite regime also works, and it also generates the signals that I'll tell you about, but they're just more complicated to track, so we didn't look at that. And we also assume that higher order friction terms like transition radiation are negligible, which again is a reasonable approximation if your terminal velocity for the bubble wall is, if the gamma factor is just some order one number, but if the walls are accelerating even faster, then you would have to worry about these higher order effects that might become more important. Okay, so then we think we have scenarios where all of the energy released in a phase transition can go into particles. And the next question to ask is, what happens to these particles when they gain this energy and become massive in the broken phase? So in the bubble frame, it looks like these particles are very energetic. They come in, they enter the bubbles, and they slow down. But if you think of this in the plasma frame or in the cosmic frame, it's the opposite, right? So you have particles that are just sitting there. You have a very energetic wall that comes in and hits it and makes it massive. And the consequence of that is the wall is actually giving energy to the particle. And as a consequence of that, the particle sort of is getting dragged along with the wall. And so you can look at what the resulting configuration is. We did this for a bunch of parameter choices. So mass over temperature is 1, 2, or 3, and the velocity of wall correspondingly is something close to the speed of light. And so what we saw was that depending on how massive these particles are and how fast the ball is moving, you get an accumulation of these particles close to the bubble wall. And so you can see that there is a distribution of these particles inside the bubble, this distribution goes all the way to the center of the bubble, but it dies down once the distribution is close to the wall. And the more massive the particle is, the sharper this peak is, right? So the more dramatic this effect is of these particles getting dragged along with the wall. So the outcome of this exercise is that when these particles get massive in the broken phase, they form these extended particle shells that extend all the way to the center of the wall, but most of the energy is concentrated close to the wall in some shell that is, say, some order 10% of the size of the bubble. And these are shells that then just expand as the bubble expands. It just follows the expansion of the bubbles. Right, so what we want is for these particles now to be non-interacting or feebly interacting. What that essentially means is that we want these particles shells, especially when these bubbles collide, to not interact in any meaningful manner. So we just want shells that pass right through each other without even noticing each other. They don't interact. So what this means is that these particles essentially have to have no interactions over the time scale of the phase transition. The condition for that is that if they encounter some number density, t cubed, of particles in the course of the phase transition and have some cross-section sigma, then over the time scale of the phase transition, which is also roughly the size of the bubble, if the bubbles are moving at the speed of light, this product of these three terms has to be smaller than 1, right? And if you satisfy this condition, that means that an average particle in your bubble will not scatter with anything else over the course of the phase transition. Now, does this actually happen? So this depends on your model, of course, but there is an unavoidable cross-sections coming from the fact that these particles get their mass from the background field that undergoes the phase transition. So there is this unavoidable interaction by virtue of that, which means that it can scatter with these background field scalar, or it can self-scatter with itself, mediated by these kinds of diagrams that are mediated by the scalar. And so if you wanted these kinds of interactions to be negligible over the course of the phase transition, then it becomes sort of tricky, right? Because so we know that if you want an interaction to be small, you want a small coupling or a heavy mediator. The trick of making the coupling small is that also controls how massive your particle is. If your particle is not very massive, then you will not saturate the energy release in the phase transition. So you have to have some interplay of making the coupling small while making the web of the field large, so that in the end of the day, what works is the web needs to be a few orders of magnitude larger than the temperature of the phase transition. And then the coupling similarly needs to be small, such that this product, this S web over G cubed T, is a number that is greater than about 10 to the 6. So you can play around with numbers. It is doable, but it is not very generic, but it is possible. Well, what you can think of instead is the possibility that these particles are not non-interacting or feebly interacting, but they decay into particles that are feebly interacting. So imagine that this particle that became massive through the phase transition could now decay into some particle Y through some small coupling epsilon. And you want this decay to be rapid over time compared to the time scale of the phase transition, which gives you a condition on how small this coupling can be. But now that you have just a small coupling, these particles will only self-scatter with themselves through this small coupling, right? They self-scatter through their parent particles at prime. They do not talk to the scalar field necessarily, and that this coupling does not necessarily need to be big because these particles are not getting their mass from the phase transition. So you could end up in this kind of scenario much more easily into final configurations where all of the energy has now gone into some feebly interacting particles. So for example, for setups like this, you can have a coupling that's very small of order 10 to the minus 6, 10 to the minus 5, 10 to the minus 4, and then all of your other parameters can be somewhat reasonable, and this works more easily. You can also think of other ways of doing this, right? So for example, it is known that when particles cross into bubbles, there are higher orders scattering processes when the particle goes off shell and can now actually produce much heavier particles. Or when these bubbles collide, you can think of scenarios where the collisions are so efficient that the collision will just give you particles that are otherwise feebly interacting. So I won't go into the details, but you can think of other ways where you can satisfy this condition where all of the energy ends up in particles. But let's ignore these kinds of model-dependent details for now. And so let's just look at what happens now in a system where all of this energy has now been transferred to these kinds of particles. So this kind of simulation is both easy and difficult. The difficult part is that these particles are really individual degrees of freedom, right? There's no collective behavior that you can ascribe to the full collection of particles just because they don't talk to each other. So what you would naively have to do is you start with a thermal bath, you track every single particle as it enters a bubble and gains some momentum kick, and then you track how that particle evolves through the rest of your simulation, which is a very tricky thing to set up. So what we came up with instead is the sprinkler picture, which optimizes how you track these particles. And the key insight of simplifying this problem is to realize that you can think of each point in space as a source of particles. And this source, the sprinkler, turns on when a bubble passes through it. So when a bubble passes through it, it turns on the sprinkler, and then it sprays particles in the direction where the bubble hit it, right? So the sprinkler turns on at a time and in a direction that is given by when a bubble passes through it. But otherwise, the spectrum of these particles that it injects is universal. Every sprinkler will inject the same spectrum of particles. It is determined by the details of your particle physics model, like the mass and the wall speed and so on. But otherwise, it's a fairly universal thing. So what you need to do is basically run a simulation that tells you when these bubbles, this nucleation history simulation that tells you when each sprinkler in the universe turned on. And after that, the rest of it is very easy. To calculate the final energy momentum distribution of all of these particles, you basically just add up all the sprinklers, and that gives you the final answer that you're looking for, right? So unlike other simulations of phase transitions, gravitational wave signals, where so Mark went into a lot of details about this. If you have sound waves, you have to run hydrodynamic fluid simulations. If you have bubble walls, you have to resolve really small differences in how the scalar field gradients work on really small scales. So this kind of simulation is a lot easier because you don't have to worry about details like that. You just have these sprinklers, you add them, and you're done. So then we do that, and then I can show you a simulation of what comes out of this exercise. And so what you see in the simulation is that you have some bubbles of true vacuum that are now nucleated and growing in a background of false vacuum, right? So the color distribution tells you, going from blue to yellow to red, that the particle densities are increasing in that direction. You should ignore the red dots, they're just numerical artifacts. But otherwise, you see that there are sort of these bubbles that have particles inside them, and you kind of see that the color is darker in sort of an extended shell that is closer to the bubble walls, which tells you that there's a profile of particles that is more peaked towards the edges of the bubble, but they do extend all the way throughout the bubble, but they're just denser towards the outer edges. So if you run the simulation, this is what it looks like. And so these bubbles grow. As these bubbles grow, these particle shells also grow, and eventually all these bubbles reach each other, they percolate, and this is when the phase transition ends. And so I invite you to pay attention to two things in particular in the simulation. Let me run it again. One is you should look at how the thickness of these particle shells increases as these bubbles grow. And the other is what happens when these bubbles cross each other. Do they interact or not? And so you would see that as these bubbles grow, the shells will also grow proportionally. So these shells are not finite size objects, right? They're basically free objects that grow. And the other thing you notice is that when these bubble shells or these particle shells meet each other, they don't interact in any meaningful manner. They just pass right through. It's like they don't even see anything else. They don't even notice anything else. So this is what comes out of configurations like this. Just as a comparison, you can compare this to a similar simulation for sound waves. And then I invite you to also look at similar aspects of it. And so here you would notice that the sound shells are much thinner than these particle shells. And the other thing to notice is that when these shells meet each other, there's some non-trivial interaction that happens at the interface, right? So the fluid shells actually interact with each other. And so I should mention that these are 2D projections of 3D simulation. So if you see bubbles nucleating inside other bubbles, there's no weird magic happening there. It's just a projection in a lower dimensional plane. Okay. So those are the two. And so just to collect the main differences between the two cases, in the case of feebly interacting particles, what you have is a configuration where there's really extended particle shells that are very loose objects that don't have a finite size. As the bubbles become bigger, they also keep getting bigger. When they cross, they don't interact, they just pass right through, and they keep getting more and more diffuse. And because they don't interact, the energy conservation is very trivial, right? You just, to calculate the total energy in the universe, you just superimpose the energy that is coming from each bubble. So you just add them linearly. Whereas for sound waves, the situation is very different, because now you have these very sharp sound shells that interact when they cross. And so the hydrodynamic fluid equation will tell you that you can't just trivially superimpose the energy density of these objects. What you have to superimpose instead is the velocity of these fluid shells. And because of that, the total final energy density is something that is not trivially just additive. And so even by eye from these simulations, you can see that these two are very different configurations, right? So then let's step back and understand the physics of what happens. So consider a bubble that is expanding, and then consider another bubble where I don't have any features shown that it is approaching. So in the first bubble, you have particles that enter into the bubble and collect into these shells, in these extended shells that are close to the wall of the bubble. And this is a very spherically symmetric system. And we know that spherically symmetric things do not source gravitational waves, so there are no gravitational waves, right? And what you have to do to generate gravitational waves is to break this spherical symmetry, which might sound confusing because I just told you that these shells don't interact at all. And so when they pass each other, they essentially don't even see each other. So you might think that these systems continue to be spherically symmetric. But the insight is that even though these shells don't interact with each other, what happens is that there is an asymmetry in the direction in which the bubble expands into another bubble versus a direction where the bubble is expanding into the false vacuum, which is that in the directions where the bubble expands into the false vacuum, you're still accumulating particles and converting them from massless to massive, which means that you get an accumulation of particles on these particle shells, and you keep growing in energy density in these directions. But in the direction where you're expanding into another bubble of true vacuum, these particles are already massive, which means that now there is no energy transfer to these particles. So in the directions where you grow into another bubble, your energy density on this particle shell is now smaller than in the other directions. And therefore, you've broken the spherical symmetry of your system, and you're ready to start generating gravitational waves. And then you can look at what the gravitational waves sourced by these kinds of setups look like. And it turns out that the signal is a fairly universal shape, which is interesting because it seems like it doesn't really depend so much on the parameters of your microphysics. So here I show you 3 different sets of simulations for 3 different sets of masses and wall velocities. And the spectral shape turns out to be fairly universal. In the IR, it seems to grow linearly with your momentum, with your wave number. And in the UV, it gets a 1/k² drop. This is what we see coming from the simulation. But the more interesting question is, how large are these signals, and can you actually see them with experiments? Right? And here is a plot to sort of answer that question. And so all these colored dots are what come out of our simulation and we've chosen cases where the mass is 3 times the temperature of the phase transition and the wall velocity is 0.99 of the speed of light. We've chosen an alpha parameter, which is about 0.23. And so all the dots are coming from simulations, and then we just extrapolate them to higher and lower energies, to lower momenta. And in particular, we've introduced by hand this break that goes from a linear k to a k³ in the deep IR when it crosses sort of the Hubble scale, because beyond the Hubble time, we expect that these correlations will no longer exist. And then it just becomes white noise, which gives you a k³ kind of shape, right? And we don't have the expansion of the universe in our simulation, so we just have to put this in by hand. And so you can see that for a bunch of different parameter choices. Was there a question?
You have 10 minutes left, including discussion.
Perfect. I think I need 5. Anyways, so now we've plotted this for a bunch of different choices for the temperature of the phase transition and the duration of the phase transition, right? Beta over h and t. And so for a TeV scale, you see that it gives you something that is interesting for LISA. For PeV scale, you get something for the SIGO and BBO. For tens and hundreds of PeV, you go into the regime of the Einstein telescope and the Cosmic Explorer. And so you see that overall, this is a pretty interesting signal that you might see with all of these detectors. And for comparison, I've also shown a sound wave signal. This is the solid blue curve, and it uses the same parameters as this blue dotted curve. So you should really be comparing those two, because those come from the same underlying parameters, but in one case, you convert energy into sound waves, in the other, you give all of the energy into feebly interacting particles. Okay, so let's zoom in and compare the two, right? And so for any signal, the three interesting sort of parameters are where it peaks, what the shape of the peak is, and what the amplitude of the signal is. And so the peak seems to be at a lower frequency compared to a sound wave signal. And that sort of makes sense because the physical scale that is relevant for these FIP particle shells is sort of the size of the shell, which is comparable to the size of the bubble. Whereas for sound waves, it is known that it peaks at about an order of magnitude higher than what the bubble size is, and therefore the peaks are off by about an order of magnitude. The peak of the signal seems to be broader for these FIP shells. It has a plateau sort of that scales as linearly with K in the IR. And so because of that, it seems to have a broader a peak that is not in the sound wave signal. So the sound wave signal also has a linear peak, by the way, but it is something that is much smaller. It only occurs between the size of the sound shell and the size of the bubble. And so it's not as broad as it is for these particle shells. And finally, the amplitude also seems to be comparable to what you get from the sound waves signals. And this is interesting because these particle configurations apparently are very efficient at storing their energy, right? Once you convert all of these energy in the phase transition into these particle shells, they don't interact with anything. So there's no energy loss mechanism where you lose strength in your signal because your energy is getting translated into other things that are not so useful. So then finally, you can fit the signal with some simple formula. So the first two parameters are pretty standard, right? There's a dependence on the duration of the phase transition, beta over h. There's a second power to it. The second thing is this scaling with alpha squared that you see for most sources, which basically tells you that if you increase the strength into your phase transition, the signal usually grows by the square of that. There's a spectral shape, the final thing, which tells you that it grows linearly in the IR as a 1 over k squared in the UV, and the peak is roughly at the size of the bubble, 0.77 times the size of the bubble to be precise. But all of this underlying physics dependence is in this parameter k bar, GW. This is the model dependent piece where all of the dependence on the mass of the particle or the speed of the wall goes into. And it turns out that for large-ish boost factors, it approaches a fairly universal value. But for very small boost factors, there are some weird wiggles that we understand as coming from the fact that the particle distributions are usually not very useful for generating gravitational waves if they're not moving very fast. But it turns out that for larger boost factors, you can use a very simple fit formula that you can just put into this. And so if you ever have a model where you think your energy might be going into feebly interacting particles and you might suspect that there are gravitational waves being generated by that, you don't actually need to run a simulation, right? You can just open our paper, use this formula, plug in, calculate what this piece is and just plug it in, and then you have your signal. Okay, so that brings me to the end of my talk. So just to summarize what I told you, right? So first order phase transitions are, of course, very attractive sources of gravitational waves from the early universe. And so far, most of our attention has been at whether these gravitational waves are sourced by bubble wall collisions or through sound waves and turbulence in the plasma. But I've told you of a scenario that is qualitatively different from them, where all of the energy instead goes into particles that are feebly interacting. So there's no collective behavior for them. You just have to treat them as individual degrees of freedom that don't interact. And so what we saw was that these configurations can nevertheless generate gravitational wave signals that are fairly sizable. You might be able to detect them with future detectors. They're at least as strong as the other conventional sources. And they're also qualitatively very distinct, coming from the fact that the underlying physics that generates them is very different. And finally, we have a simple analytic fit formula that you can use to estimate what the signal will be like for a model of your choice. So I think that was all that I wanted to tell you. Thank you for your attention, and I'm happy to take questions.
Thanks a lot, Bibhushan, for this very interesting talk. It's not every day that we hear about a new source of gravitational waves, after all. So are there questions to Bibhushan? As usual, there is one question in the chat by Jason Balls. Do you just want to unmute yourself and ask directly? Okay.
It's not working, but I can see it.
I'll read out the question. The question is, the IR-UV scalings with frequency seem similar to the thick wall case from the Hindmarsh simulations with only the scalar. Is the amplitude similar or different?
I would have to look at what the amplitude is like for Mark's simulations. I don't know this off the top of my head, but I can tell you, right, that the particle shells for us give an amplitude that is comparable to a sound wave source. And so if Mark's simulations also find that the amplitude is similar to what you would get from sound waves, then they might be similar.
Mm-hmm.
If I may, so this is sort of connected to the question that I wanted to ask, which is, so this is kind of like the bulk flow model, pretty much.
This is kind of like the bulk flow model, except with a very thick bulk, right? So the bulk flow model takes them to be infinitely thin, but the interaction is then the same in that the bulk flow model assumes that these energy shells don't interact, they just pass through and then dilute as 1/r². And in principle, the same thing happens for our configuration. The only difference is that now these particle shells are very extended and of the same size as the bubble instead of being infinitely thin.
Right. Well, so then I would expect it to be the same as in the simulations by Mark, because well, if you just have a scalar, then the scaling is R2 minus 2, is it? Well, it's the same as in the bulk flow model, pretty much.
It's the same as in the bulk flow model, for sure. Yeah. So if Mark's simulation is
because it should be R2
right.
minus 1. So maybe not exactly the same as in the scalar case.
Yeah, I can maybe make an observation. There is that the IR power is different because yeah, you here the in the scalar case there's a clear k cubed spectrum generally, whereas yeah, you have this characteristic bulk flow k to the 1 caused by the sort of expansion of the shell and consequent decrease in the energy density. So, and I'm actually, embarrassingly, I can't remember what the range of power spectrum on the UV side was, but don't remember them reaching -2. But.
Yeah, I thought it was different. It was even sharper than that. Well, not sharper, but a lower power, I want to say, right?
I think so, but I'll have to check for because it's the thick wall case. Yeah.
Right.
The thing that I showed was the thin wall case.
We got another question in the chat from Debashish Bora. Do you want to ask the question directly or shall I read it out?
Yeah, I can ask.
Yeah,
can you hear me?
Ahead. Yeah, go ahead.
Okay. Yeah, so you said that all the energy of the phase transition is transferred to the feebly interacting particles. And then they probably decay to the actual dark matter through the sprinkles and all. So do you have constraints from Lyman alpha on the free streaming dark matter, or is it like cold or warm dark matter?
Yeah, so this is actually a dangerous regime because, of course, if you want to see an observable gravitational wave signal, then you're starting with a lot of energy in the dark sector, right? Which your alpha is essentially 1 or something that's not too much smaller than 1. And if you convert all of that energy into particles, then if you just converted all of that into dark matter, you would just overclose the universe. And so what we assume in our paper is that these particles at some later time after the phase transition completes just decays into standard model. And so all of the energy just goes into the standard model. Otherwise, if you kept all or most of that energy in a dark sector, then you would get these strong constraints, I think, and they might be impossible to satisfy.
Okay, thanks.
There's a raised hand by Arnab Dasgupta. Please go ahead.
Yeah, hi. I'm just curious. So in your entire discussion, it was fairly model independent one, right? So you didn't consider a dark sector or any other model specific thing, because if you're saying feebly interacting, it has to be in a totally different disconnected sector, right?
Right.
So basically what you're saying is that you have a totally dark sector, which which breaks the symmetry and gets the phase transition, or you're talking about the electroweak phase transition? Which one you're talking about here?
I'm talking about some dark sector. Yeah. So in
some dark sector phase transition, right?
Right. Yeah.
Okay. So basically that one.
Precisely because in an electroweak phase transition, we know that all of the particles that interact through electroweak interactions are very efficiently interacting at that point, right?
Yes.
And so what you would need is for something to then very rapidly decay into some feebly interacting particle, but we know that at least for the standard model, there is no such decay channel for any of the particles we know of. So what we had in the back of our minds really was that this was some dark phase transition.
Yeah. So in a way, you're saying that some U1 dark or some sector, but that is basically if connected to your standard model has to be some Higgs portal or something like that.
Sure. Yeah.
Yeah.
Exactly. And especially since we assume that all of these particles eventually decay into the dark sector, right? There needs to be some coupling, sorry, into the standard model sector, then there does need to be some coupling that connects those two.
Yeah, because exactly.
Yeah. But whether it's strong enough to, say, thermalize the two sectors in the early universe is a different question. And I don't think that's a necessary condition.
Yeah, sure.
Yeah.
Perhaps I could ask one question, which I think is because I missed it from the talk. But how does the phase transition happen, and what are the thermal effects that drive it?
We were agnostic about this. We just started with some parameters, right? The usual alpha and beta over H and temperature, and we just ran with that.
So there's some sort of sector beyond the fields that you're considering, which is interacting to make a plasma.
Right, indeed. Yeah. So most likely you have some scalar, some dark sector scalar. It has some thermal corrections, right? Coming from the fact that you have a plasma, and then when those thermal corrections change the potential significantly, then you undergo the phase transition, and right, the usual.
So I was wondering, is there any sort of extra tuning going on, which because if the phase transition scalar is connected to a plasma, then there will be induced radiatively induced couplings to the particle that you want to be feebly interacting.
Yeah. So at least in this example, right? Yeah, so this is sort of the limit where I think all of those concerns go away. So if you just have, right, so if you have a particle that just decays into your feebly interacting particles, then the only obvious connection between, right, your feebly interacting particle and the dark sector is this decay coupling, epsilon, right? And so there does not necessarily need to be any other coupling, any other way that this particle talks to the dark sector that you had a phase transition in. And so in this limit, at least, you wouldn't worry about any radiative couplings.
Okay, thanks.
But more generally speaking, of course, that is always a possibility. And that happens more likely than not.
So we are already in the middle of some very interesting discussion. So I'd say that we formally move to the panel discussion, which means that we first thank Bibhushan again for his very interesting talk. So thanks a lot.
Thank you.
Now, I'm supposed to chair the panel discussion. So I guess the best way to do that is by first introducing the people who are on the panel. I hope they're all aware that they are on the panel, which is basically the speakers of today. To the extent that they could make the time work, because as you know, this is a workshop across all the time zones of the world, so not everyone could stay, unfortunately. So the panelists are Mark Hindmarsh, whom I already see. Mike Baker, unfortunately, couldn't make it, but to some extent, I think I can also answer some of the questions you may have about his talk. Then I don't see Graham online. I do see Marike and of course Bibhushan. And in addition, we have Arnab Dasgupta as a panelist today. So thanks a lot, Arnab, for agreeing to be on this panel as well.
Thanks.
So to get us started, I've prepared basically one slide showing what we've been talking about today, or what we've heard about in the 5 excellent talks. So we first heard a talk by Mark Hindmarsh on gravitational waves from phase transitions, then dark matter at phase transitions by Mike Baker, then effective potentials from tadpole resonation by Graham White, then the electroweak phase transition in EFT by Marieke Postma, and now in the end, gravitational waves from feebly interacting particles at phase transitions from Bibouchan. And I think all of these talks have provided lots of answers, but of course, all of them have also given an outlook into the future. So what I have on this slide is just some notes I took on this outlook. For instance, so in Mark's talk, one of the unanswered questions is still, what is the power law at low K? So that is certainly something that will be very, very interesting from an experimental point of view. So that's certainly an answer we're looking forward to. Also, what limits the wall speed in supercooled transitions? We've talked about the fact that supercooled transitions are not quite accessible simulations yet, and but it's clear that there is something that prevents walls from running away, especially when there's extra interactions and particle production. But there's some disagreement in the literature as to what that limiting velocity is. And finally, from a more practical point of view, one of the elephants in the room is foreground suppression, as illustrated in this plot here on the upper right of my slide. So in order to potentially see a stochastic gravitational wave background in the future, we need to have good control of the foreground sources. And one of the questions that Mike's talk has raised is, can the phase transition needed for primordial black hole formation be realized in concrete models? So Mike has shown that in principle, if you assume a phase transition with certain properties, then you can make black holes. But what is still missing is the connection to, say, a specific particle physics Lagrangian. From Graham's talk, we've seen a very interesting first step towards improving our calculation of effective potentials and thereby improving the predictions for the parameters of phase transitions from such Lagrangians. And of course, the next steps there could be to apply this formalism to other models and to see if this formalism can be taken further so that it not only provides the same accuracy as other mechanisms, but at lower computational cost, but whether it can actually also do things that other methods cannot do. Finally, from Marike's talk, one of the questions I took is that, well, it seems that higher order corrections are usually not suitable for generating first order phase transitions from a theory where the low energy degrees of freedoms do not do so, but it's not completely impossible to do this, especially in dark sector phase transitions. So under what conditions can this happen, for instance? And finally, what I found interesting about Bibouchan's talk is that, in a sense, the models that Bibouchan looked at were not so dissimilar from some of the models we had seen in earlier talks, for instance, in Mike Baker's talk. So a particle gaining a large mass during a phase transition. So there may be interesting connections there between the two talks. And I'm not sure how we best want to go about the discussion, but I first propose that I ask the audience if any of you has specific questions that they would like to ask to either of the speakers that may be left over from the day that you didn't get a chance to ask after the talk. And then now would be a good time to ask those questions. I think I need to quickly go away from full screen mode, otherwise I can't see the list of participants because I can't see my mouse pointer. Yeah, since I don't see any immediate hands up, maybe maybe I get started. Maybe by coming back to Mark's talk indeed. So in a sense, Mark, your work is at the foundation of much of what is being discussed at this workshop. Everyone refers to your simulations when they make predictions. Yeah, so you showed these open questions, some of which I've listed here. What is your take on what it would take to answer these questions? For instance, what would it take to understand the power law index at low K, say? Is that something that requires more computing power or more theoretical work, or what is your outlook to the future there?
Yeah, I'm not. Yes, in principle, you would try to. You could say just find a bigger computer, but that's actually quite hard. There is a bigger computer which we're learning to use here in Finland, which has got thousands and thousands of GPUs, but that will take some time to exploit that. Yeah, but the other thing that one could do is not sort of test it directly, but test the theory on which the K to the 9 is based, which rather than actually try to do the whole, simulate the whole phase transition. But the theory on which it's based is basically colliding sound waves with a particular power spectrum. So there's a particular relation between the power spectrum at low K between the velocity power spectrum and the gravitational wave power spectrum.
So you mean you run a simulation where you inject sound waves by hand and then see how they evolve?
And then see how the gravitational waves evolve. Yes, that's right. So I'm happy to say that we're not the only people doing simulations anymore. There's another group in Stockholm with Axel Brandenburg, and of course I mentioned about Ryusuke Jino and Thomas Konstantin and collaborators, and that's who's so they were trying to. They had some bubbles and so on, and were operating with the real power spectrum. But I think one could just inject something with a much shorter wavelength, but nonetheless had various power laws and check the relationship between the power laws and the gravitational wave production.
My understanding is that also a group in the US around Ben Safdie is getting interested in this topic. So they have in the past run numerical simulations that you might be familiar with, simulating the axion string network and how it evolves over time scales.
Yes.
My understanding is that they are trying to apply that technology also to problems related to gravitational waves. So I don't know the details because I'm not directly involved, of course.
Yes, no, one of the things that somebody mentioned was that adaptive mesh refinement, whether that might increase the sort of dynamic range. So, but yeah, no, axion strings is another thing. But too bad there's no. But the gravitational waves are probably not large enough to be relevant for this conference.
In terms of, so let me ask, in terms of other sources of gravitational waves, like for instance, the one that Bibushan talked about just now, how easy or difficult would it be to include that in your simulations? I've seen, Bibushan, that you have done some simulations of your own, right? But I think those simulations did not include potential feedback on the plasma, right? Or is there such feedback, or can you just argue that because of the weak couplings that you have, this feedback can be neglected?
Exactly. So this is a limit that maybe is not realistic, right? So we were working in the limit where all feedback can be neglected and the system is completely non-interacting. In any realistic scenario, you would expect some combination of both effects, right? And so then to get the interplay of the two behaviors together would require more fancy simulations.
But wouldn't it be, you just need to compute the efficiency in some model. So it's like bubble collisions versus sound waves.
Indeed. Yeah. So really some fraction is interacting in a certain way, another fraction is interacting in a different way. And then, you just have
I would assume that most of the energy goes into one source.
Indeed.
Probably.
Yeah.
Such that for some values of the coupling, you get sound waves, and then that cuts off, and eventually you see mostly the free streaming part.
Yeah, and in fact, another interesting sort of direction it can go into is to ask what happens when these feebly interacting particles just happen to decay while the bubbles are colliding, right? Because now you convert all the energy from feebly interacting particles back into interacting things. And so what you would see, for example, in the signal I showed you was that the IR part will just get exponentially shut off as these particles decay. But then instead, where that goes into is a buildup of sound waves. And so then you actually have not just a superposition of the two signals, but one of them actually gets distorted in a more meaningful way, right?
Can I ask you, Bibhushan, to what extent did you include the feedback that particle production has on the dynamics of the bubbles?
Oh, there's essentially no feedback, right? It's the bubble just has a constant wall velocity, and it just
okay. So you're assuming that the bubbles they have reached equilibrium and they're just expanding with a constant velocity, and then
and so for the gravitational wave simulation, indeed, there's in fact no bubble wall, if you want to think of it like that, right? Because the energy in the bubble wall is so small compared to the energy in these particles that you can just forget about it.
But since you have these particles, this increased particle density in front of the bubble wall, and that density increases throughout your simulation, shouldn't that lead to some changes in the pressure and therefore lead to some changes in the wall velocity?
So this depends on the parameters, right? So what we had was fairly large bubble wall speeds, which means that anything that gets reflected goes off with a much higher velocity back into the plasma, right? And if these are feebly interacting particles, they will just go on to the next bubble that approaches them and probably will enter those because now they have more energy in the system.
But
so
you also, didn't you assume they don't exist? I mean, that there's nothing reflected?
Yeah, we did. But I'm saying even if there was a reflected fraction, they don't just accumulate in between the bubbles. They might just enter into another bubble and change the distribution of particles inside the bubble rather than just building up outside.
No, so
of course, right, when the bubbles merge, no?
No, but we did the simulation, right? So together with Hardy, Verma, and Ville Vaskonen, we did the simulation of that exact setup.
Right.
And what happens, because what you did sort of corresponds to choosing a detonation solution. If you didn't do that, then what you would see is that there is a profile that looks more like a deflagration or a hybrid, meaning that there is a little bit of the accumulation of particles in front of the wall.
Yeah, but I guess what you had was wall velocities that are not super big, right?
Well, they were similar to yours in the sense that go up to close to 1.
Yeah, so of course I haven't done these simulations, so I have very little insight on what actually happens. I just assume that if they're not interacting in the symmetric state, then they are free to just shoot off at a higher velocity and enter another bubble, but there might also be a significant buildup. So that might be possible.
No, I mean, they do shoot off, but it just looks like, well, you accumulate them in front of the wall. They don't acquire...
Yeah. The wall itself is also traveling at a very high velocity, right? So it's not like they can go off infinitely faster and just leave the wall. It will just follow, it'll just create a front in front of the bubble walls, of course.
Yeah, exactly.
Yeah.
So
although somehow...
Yeah, go ahead, Marek.
I was just going to say that somehow if it's if summing up all those shells still looks like bulk flow, then I would expect that if there is a shell outside, it would also look like bulk flow somehow, because it all starts behaving in the same way after the collision, just going as r to power -1.
Yeah, so I think that would be true. If you just have a buildup of particles in front of the wall, of course, in the symmetric phase, they are massless, but eventually they have to become massive, right? And so the question really is what happens when they enter a bubble, but I don't think they'll do anything qualitatively different from what I've shown you before. The profile might look a bit different, but in terms of their behavior, like you said, it's just going to be bulk flow with a shell outside the bubble instead of inside.
Well, that's for strong transitions. It's probably, I mean, so what Mark was saying about droplets will be reflected on this in the sense that if the friction is really big on the wall from the particles accumulated, then I would expect that the walls would actually tend to sort of bounce back when the friction becomes too big. So there would be some droplets remaining. So there will be a significant back reaction on the walls when they're trying to squeeze the remaining false vacuum. which is something that we're looking at with our simulations at the moment. Well, but it all depends on the parameters, so I don't really have a concrete example for you.
Yeah,
but there is a maximal compactness you can reach. That's what I can tell you for sure.
That's the effect that Mike took to the extreme in his talk, right?
Yeah, then you became black holes, right?
Yeah.
Right, so, but that's the question. Can you reach the compactness? Because you assume that the wall has a constant velocity, right? So there is no back reaction.
Yeah, I think so. There are some arguments in Mike's scenario for why assuming a constant velocity is a conservative assumption. But I agree that that's one of the main weaknesses. And I'm allowed to say that because I'm on the paper. So Bibushan, in your scenario, so of course, you had this assumption of very feebly interacting particles, but assume that the particles interact more strongly and so thermalize over a certain time scale. Wouldn't you still have an effect that some energy density gets dragged along behind the bubble walls? So imagine you have a particle that enters the bubble. It gets relatively heavy. And then, yeah, it quickly equilibrates with the surrounding plasma, but still that takes a certain amount of time. And since your phase transition is proceeding relatively fast, shouldn't you still end up with a somewhat higher energy density just behind the bubble wall as compared to the regions deeper inside the bubble?
Yeah, indeed. And these are the detonations and deflagrations that you see in the sound waves, right? It is a buildup of exactly this of energy that is closer to the bubble wall than deep inside or outside.
Right, yeah.
Mm-hmm.
Oh, but actually, I have a stupid question connected to those profiles you showed, because if T is proportional to the velocity, and this is something that worries me a little bit, because you have a radial, well, it's all spherically symmetric. So if the velocity is non-zero at r equal to 0, doesn't that mean you're creating particles at the origin somehow? Because there is radial velocity, at all possible radii.
Sorry, what do you mean you're creating particles at the origin?
Well, because the velocity field, so in plasma, the velocity always goes to 0 at some point. But for you, it seems that the velocity field is always non-zero, even when you go to the center of the bubble, meaning that there are particles flowing out of the center of the bubble all the time.
Yeah, this is just the limit of what we see in the rest of the bubble, right? And so indeed, so these would correspond to particles that entered with a lot of energy, right? So this is the end of the Boltzmann tail from outside, if you want. So these are really energetic particles anyways. And so when they enter the bubble, they already have a lot more energy than what is needed for their mass. And so even once they enter the bubble in the frame where the wall velocity is 0, they would penetrate and essentially keep shooting in without losing any velocity, right? So this is the limit of the exponential tail of the distribution. And of course, when you boost back to the plasma frame, then it looks like these are now close to the center of the bubble, but yet moving outwards because, yeah.
Okay.
So yeah.
There is maybe to change the direction of the discussion a little bit. There's one topic that has already been discussed today, and that I have the impression has gained a lot of traction in the literature recently, and that is supercooled phase transitions. So there was already some discussions after Mark's talk about why it's particularly difficult to simulate those phase transitions. Then, of course, Mike has used those phase transitions. I was wondering if so Graham isn't here anymore, but in the formalisms that maybe someone else from the audience is knowledgeable and can answer. So I was wondering if the formalism that Graham showed and the EFT formalism that Marike discussed, if there's anything special about supercooled phase transitions, like is the formalism particularly well suited there, or is it particularly poorly suited? Yeah, since there seems to be a general theoretical challenge in dealing with supercooled phase transitions, even though they are quite interesting from a phenomenological point of view. So I don't know if Marike, if you're still there, for instance, is there anything from an EFT point of view that can be said about supercooled phase transition? So here I'm not thinking about generating the phase transition via higher order corrections, but for instance, using EFT to deal with this large separation of scales that we typically have to deal with in supercooled phase transitions.
Yeah, I'm not so knowledgeable about the supercooled phase transition in the type of extra interactions you would get, in the sense if they're also just power law or that you give other options, right?
So I'm thinking about if I imagine that there is if I have some direction in my scalar potential that has a very shallow minimum at a very large field value, is that anything where a useful EFT can be developed? I'm really not an expert at all, so I'm more asking the questions into the to all of you. If there's anyone who has any insights on that could be a very interesting thing to do.
So, actually, we are looking at the moment at this kind of description. So, I'm interested in models with classical scaling symmetry. So exactly potentials which have a minimum that is far away from the field origin.
And is generated through the Coleman-Weinberg mechanism then?
Yeah, exactly. And then, the question is, can you improve the description using, let's say, dimensional reduction? And that's something we are working on. But the problem that you face there is that when you look at, let's say, around the temperatures at which the phase transition proceeds and around the minimum of the potential, the high temperature expansion doesn't hold anymore there. So for sure, you cannot just use dimensional reduction everywhere, but most likely you can do it, in some limited range of fields and temperatures. And hopefully I'll have some more results in the near future, but for now I don't have them yet.
Do you have an idea of whether the formalism that Graham talked about today would be useful there? Because he emphasized a couple of times that once you solve the gap equation numerically, you're no longer bound to use the high temperature expansion, but you might just do it at arbitrary temperature. But I understand that's not the formalism that you are using. You're using dimensional reduction, right?
Yes, exactly. But I guess it could be done. Actually, in a paper that we did some time ago, we did some kind of gap equations, but I don't think it was exactly what he meant here. I would have to look at it closer. But there, solving those gap equations didn't really change that much the results. But it might be we were not doing it the best possible way, I would say. But as I understand it, it's like by solving those gap equations, you just free some higher order contributions into your effective potential. So it's kind of related to the dimensional reduction. So
so
I can see Philip there, so maybe he'll say more. But
I have to say the topic was new to me, so this was the first time I heard about this approach today from his talk. So.
Yeah, sorry, I also want to have a quick comment on that. Especially dimensional reduction is I mean, as in its current form, of course, you're taking the high temperature limit everywhere, and like the thermal integrals and everything. And then if you do that, of course, then you can't cover the whole range of a broad temperature range, basically. But I think it's actually possible if one would just do the matching with actually the full thermal integrals, such that they actually appear in the matching relations. So there is a possibility to extend the validity of the high temperature expansion in such a way that you can cover a larger temperature range. And that is, I guess, the real question, to figure out if you can go like much lower in temperature and really reach regions of supercooled phase transitions. But again, this is really a topic that needs to be, I guess, analyzed and really studied properly, because at this point, I guess in this case it hasn't been done before. But there's of course some obvious things to do at this point, and this is what I just said. Try to extend the applicability to a larger range by keeping the thermal integrals in the matching, for example. I think this is really one of the next steps. So then dimension reduction might actually be applicable, but of course it's still an EFT. So you might at some point, if you go to lower temperatures, need more operators to cover more of the I mean, to really make it extend the temperature range of it. But again, it still needs to be done at some point. We don't know this yet.
So it's good that there's things to be done and that we have an idea of what the next steps are. That means we can have many more of these workshops.
Exactly.
Yeah, I'm not sure if this is the right place to discuss this, but one topic that I find quite interesting is the one that Mark mentioned towards the end of his talk, namely foreground suppression. What can we do to actually get rid of all the foregrounds that might hide a stochastic gravitational wave signal from detection? So I'm not sure we are the right group of people to discuss this, but I nevertheless like to bring up this topic. So my understanding is that, yeah, among the main foregrounds are these galactic binary systems. And of course, we can try to see as many of those directly in the gravitational wave data and then subtract them off. But I was wondering if there's some sort of multi-messenger approach that can be used to do precision measurements on as many of these binary systems as possible, and then infer their gravitational wave signals without actually having observed them. Is that something that is being done? Yeah, once again, I'm asking a question here about a field that I'm relatively far from.
Yeah, I'm not really an expert on this, but I can say one or two things. I mean, yeah, so the people are actively trying to do this, at least in the general context of subtracting out signals and seeing what's left. But yeah, so saying there's an unknown number of white dwarf binaries in our galaxy. Some estimates range in 20 to 30 million, and there are sort of a dozen or something that are actually known and will be actual sources of so-called verification binaries. And there will probably be tens of thousands that will be have sufficient signal to noise ratio to be observable and therefore subtractable in LISA, which leaves so that kind of is why the graph I showed has the shape that it does, in that actually the signal, it has this funny knee. Yeah. And that knee is the thing that's left over from when the higher frequency binaries, which are the louder ones, which are the ones that will be observed, are subtracted out.
So in order to see a white dwarf binary in any channel other than gravitational waves, what would it take? Is that anything where future telescopes, I mean, non-gravitational wave telescopes, but say radio telescopes, infrared observatories can help? Or are we really, do we really have to rely on doing this all with gravitational wave data alone?
Yeah, I think it is actually, the gravitational waves will be the primary way of doing it, because I mean, I say I'm not an expert, but I suspect if they could be seen in the infrared, they would have been seen in the infrared already, because there have been a lot of infrared missions. The main problem is that the galaxy is pretty opaque in
many may be obscured,
in the wavelengths which white dwarfs shine. So so yeah, it's a thing that's under active investigation by people here in Helsinki and of course elsewhere. And of course, there is this. Lisa runs these data challenges, which as I'm sure many people know. And of course, the white dwarf foreground is one of the things that they delight in putting in and not telling anyone what it is. But the thing is that the foreground modeling is to a certain extent, we don't know what the predictions of the amplitude and the frequency spectrum are very uncertain. So amplitude, you have different models of what the white dwarf distribution of the galaxies, and the amplitudes differ by order 1 or maybe even order 10 factors.
Mm-hmm.
So
yeah, I heard the reason I'm asking about this because I heard an interesting talk recently by let me think, Emanuele Berti, I think, about precisely that topic. So about subtracting the foregrounds in LISA, and it seemed to be it seemed to be very, very difficult. So they made some progress by doing some fine-grained changes to the analysis, changing certain analysis thresholds to get a better handle on those. But it seemed like it's really tough.
Yeah, no, it doesn't. It's not something that you can do in an afternoon. That's for sure. But I suppose it's 10 years at least. Then of course there's another couple of years while it sort of gets into position and starts taking data.
Yeah, and then once you have data, of course, everything will look different. Again, with more insights on how the detector responds. Yeah.
True. Well, but a bigger problem might be the black hole binaries, which are not included in the plot. Well, to an extent they are, because those are the lines that are extended.
These lines here, right?
Yeah, because those are expected to really cut into LISA sensitivity. And their subtraction is actually much more difficult, because with the white dwarfs, you're seeing the high frequency tail, meaning that you see the collision. But with the black holes, this is, they collide somewhere in LIGO frequencies. And here, this is the inspiraling part. So this is actually like a very weak point source that is constantly radiating towards you as the binary slowly inspirals. So these are much more difficult. And actually, I think the expectation is that LISA will not really be able to get rid of that many of them by just directly discovering them and being able to cut them out of the signal.
Is there a possibility of subtracting this background on a statistical basis, given that from future runs of LIGO and other ground-based observatories will have relatively good statistics to do a population study of these binary black holes?
I've got a graph that that flashed by on one of my transparencies, which may make Marek less
Do you quickly
pessimistic.
want to show it again?
Yes, please.
Okay, then I will stop sharing so that you can.
Here it comes. And yeah, so this thing down here is so this is the LISA instrument noise. This is the sort of LIGO prediction for the confusion noise from cosmological black hole binaries. So it's actually not that significant. Of course, if your phase transition signal is down here, then it's not so good. But LISA wouldn't be very sensitive to that anyway. So I think the black hole binaries are not the main problem. It's the white dwarfs.
But if you're doing the power, because this is not the power law integrated sensitivity, right?
No, it's not. But
so if you power law integrated, you'll see that it does cut into the power law integrated one.
It may well cut into the power law integrated, yes. Yeah, but you can. I mean, the black hole binaries are sort of, as I say, it's going to affect stuff around here a bit. but it's I'm much more worried about that bit.
Well, but actually, I think it turns out that because you're able to, identify and cut out the white dwarfs, it seems that the black holes are actually causing more of a problem, because there you really cannot get rid of any of them. Because all of the power law integrated curves that everyone always shows, they do include the white dwarfs to begin with.
But according to the plot that Mark just showed, the binary black holes only become a problem once your experimental sensitivity is 2 orders of magnitude better than what we expect in LISA. So this may be a problem for future observatories.
No, because the actual sensitivity is better than the instantaneous one.
Oh wait, so this was a plot of instrument noise, not
power law integrated, exactly.
Sensitivity. Okay.
So I have a different plot that I can show, which can we just find any of the talks, because we tried to show the impact of this in a paper with Ville at some time ago. Okay, this is the plot. Let me just try and share screen. So this is how it looks like. Full screen. I assume you can see the.
Yeah.
So if you do power law integration, you see that the reach is actually some 10 to minus 13. This is the dashed line. So this is what people always show. This gray dashed line is the line, I believe, exactly corresponding to what Mark was showing. But then if you take into account the fact that so what we were trying to do here was pretty much like a power law integrated sensitivity, but from a Fisher matrix. So we were just checking which power laws you can still probe with some small error on so this is the primordial background part, with a small error on this, and then taking the envelope. So as you see, the LISA sensitivity would just be cut like this. And the reason it's cut like this is because the error on the rate actually puts the upper end of this sensitivity here. This is why it's actually even above. But this can be made better in the sense that if the error on the rate was 10 times smaller, it would look like the dot dashed line.
And that would basically require observing more mergers in LIGO.
Yes, well, probably in ET, because as you see for ET, the 2 lines are identical, meaning that you probe the rate so well that it doesn't really do anything, assuming that you can probe it better.
Yeah, what confuses me a little bit is that the gray dashed curve is below the sensitivity of LIGO according to that estimate. So it would seem that LIGO should not have seen any of those according to the gray dashed line.
But this is the so it's actually within, but the problem is, so the gray line here is all of them integrated, but the rare events that actually contribute more are very rare. So they don't, well, when you integrate it over time, it looks like it's less. But so there is some difference. So all of the events integrated give you the gray dashed curve, while integrating out the part that we've seen already, because we have some identified binaries, will give you the continuous brown line for LIGO. So there is a little bit of difference. Right.
Yeah, so it makes a big difference if you're looking for power laws, but it doesn't really make much difference if you're looking for a peat spectrum, I think, is the for which the sensitivity is much less. So.
But why is it much less for peat spectra?
Well, it's less. I mean, so you, in order to, I think probably if you wanted to do this to show what difference it would make, it would be good to use this peak integrated sensitivity curve, and that would probably give you a better idea of how much black holes remove.
Peak integrated, I'm not exactly sure, because I mean the power law integrated one is pretty good in the sense that if it tells you will see something, then even if it's not really a power law but just peaks close to it, the signal to noise ratio is still order 10. It's a few at least. So you're not making a huge error there, I think.
But for a power law sensitivity, you're assuming that you have a signal throughout your spectrum. And of course, since it's a power law, most of your sensitivity will come from the end where the power law is highest. Whereas when you have a peak, in a sense, you can see a peak as a cutoff power law. So only part of your frequency spectrum gives you sensitivity. Is that the reason, or?
Yes. Well, so that's why this plot is not maybe perfect, because it's true that when you look, so alpha is the power of the power law. So you see that the problem is peaked exactly when your signal would be have the same power, which is, well, the index 2/3 as the gray dashed line. If it's very different, then the problem is less. So this is the amplitude you need to observe something. That's true. Well, but as you see, so from the dashed line, which is what we hope would be the result if there wasn't any black hole binaries, the problem persists even for different power laws. So if you're close to the peak, choosing 0 is a good approximation, roughly. And then, well, it's still an order of a few at least.
Mm-hmm. So the way I should read the plots at the bottom is this is your sensitivity. So the higher the curve, the less your sensitivity.
Yes.
Okay.
Yeah, so this is the amplitude you can probe.
Mm-hmm. Okay, so we've had some very good discussions already. Are there any other topics that any of you would like to touch upon before we conclude the session?
Well, in the context of model building, I can just say that the conformal model has far more implications. Like, for example, like I can just quote what Vibhushan has done. Like we had touched upon feebly interacting a couple of years back. Like on what we did is a U1 dark sector in a conformal model. So, and not only that, if you go for a non-abelian conformal models there and purely Yang-Mills, then what you'll find that the gauge broken from the non-abelian sector is a natural dark matter, because that's basically it's a natural Z2 symmetry that you can get. So the interesting part was that if you really like the problems that we're facing right now, because I'm really looking into this as a model builder, because I'm totally how to say, an outsider how to get into those things. Like I just can get the parameters that you guys want and then just get the wave amplitude. That's it. But the implications are really interesting, because the scale of, or the peak of the amplitude of the gravitational wave is actually telling you the mass scale of the dark matter, to be very honest, especially in these kind of a very subset of parameters. Not only that, I guess one of the participants is Baldes. His work on relativistic bubble, where you can actually go for the leptogenesis, where we actually did a follow-up work, where the amplitude of this gravitational wave can actually correspond to the leptogenesis scale in a way. So in a way, as a model builder, I can say that conformal model has pretty rich paradigm to explore. It is pretty rich right now. But as what I can see, that conformal models has some limitations as for what can we have, like what can be said about the bubble wall velocity, because usually I think it is pretty high and it is taken to be 1 or so. It is taken to be relativistic, right? It's taken to be around 1, what I assume actually. So yeah, so that's basically what my take is as a model builder. Yeah.
So the models you're referring to, I didn't quite understand. Are these U1 models or non-abelian?
No, so I basically worked on 2 models in a way to basically explain the nanograph, which was very low frequencies. So I basically worked on U1 dark, where same what Vibhushan is that for dark matter, we basically introduce a feebly interacting dark matter because we are focusing on totally dark sector. And then on the follow-up, we basically did a SU2 dark. Now, what we found out in SU2 dark, and that can be extended to any higher gauge also, that if you just plainly look into Yang-Mill theory, SU2 dark or SUN dark Yang-Mill theory, the gauge sector which is getting broken is a natural dark matter. Now, the point is the multiplet of the SUN is giving you the number of dark matters, and the mass scale is basically will be reflected on the peak of the gravitational wave. So that is in a way, to me, it's pretty interesting that like the SUN and the dark matter is getting so much interconnected in a way. And obviously the direct detection is obviously through the portal, the Higgs portal. That's the only connection for the Yang-Mills you can go through. So yeah.
So since you mentioned that one application of these models is to explain a nanograph, right? This implies a phase transition at a very, very low temperature.
Yes, we did that. We did that for nanograph for SU2 dark and the U1 dark.
How can you hide such a low temperature phase transition from the ineffective constraint at BBN?
So yeah, so in a way, like so we're focusing on around GeV scale. So
still safe from BBN. Okay.
Yeah, it's safe. It's not that light. It's not that light. And even if you're talking about the feebly interacting, what we considered is a very milli charged because one more thing. What I found out on these specifically working on these things is that the gauge coupling turns out to be specifically the dark gauge coupling turns out to be pretty large. Actually, it turns out to be around your electroweak charge or gauge coupling. It turns out that the span is around 0.3 to 0.35, where you will actually see the phase transition happening in a way. And for example, if you go for a U1 dark sector, what Vibhushan introduced is a kinetic mixing that we also did. But since your gauge coupling is pretty large, you need to introduce a milli charge so as to, push down or make it feebly interacting in a way. So the gauge coupling turns out to be pretty high if you're focusing on conformally supercooled regime. I'm talking about only on supercooled paradigms. So, but yeah, so because the most interesting part is, the entire parameter space reduces. You don't have any other free choices because everything is connected to everything else in these paradigms. So,
but can I ask, if you're thinking of the GeV scale, then why is the peak around nanograph?
No, the GeV scale. Okay, not GeV. So we did come a bit lower than 0.1. It's not very low. It's not around keV that we came around. So it was till GeV in a way. So let me just pull out the word there. A sec. Yeah. So we did came out to around tens of MeV till 100 MeV. So the thing that we basically showed that around 10 MeV we did get the nanograph result for our work.
That's then already dangerously close to BBN. That's where BBN starts to be sensitive.
Yeah, I know. So we but that's where the feebly thing and the gauge coupling is pretty high enough. So yeah, we kind of escaped it. I just need to refresh my memory how we Because the number of degrees of freedom that you're talking about, that's where the thing gets messed up. So
yeah, I see that
yeah,
Debashish is making some
yeah, so
comments in the
Debashish, you can just pitch in actually.
Yeah, feel free to unmute yourself, Debashish.
Yeah.
Yeah, I'm not sure my net connection is very good enough at my house. So yeah, I mean, as you said, it's very tightly constrained. If it is around MeV or even below, and this paper from Wisconsin, they actually constrain the parameter space of this kind of very low scale phase transition models from BBN, as you have pointed out. And yeah, a large portion of the parameter space is actually constrained. Yeah, so it's not very easy. Yeah. That's all.
Okay, so I think our time is basically up. So I think we had some very good discussion. So I'd like to thank all of you for that. First of all, the speakers of the day and the panelists, but also all others of you who've stayed with us, who've contributed to the discussion. Thanks a lot. This was really great. I don't know if the organizers still want to say anything. My understanding is that tomorrow is the break day, and then the workshop continues on Thursday at 2:30 p.m. Central European time, with a day devoted to inflation and its gravitational wave signatures mostly.
That's exactly correct.
Okay, so then thanks a lot, everyone. I hope to see you all soon, and enjoy the rest of your day, afternoon, evening, depending on what time zone you're in. Yeah, all the best and take care.
Yeah, thank you for sharing the discussion.
Well, I made you do all the work, right? You're the participant. Okay, so take care, everyone. Bye-bye.
Thanks. Bye-bye.
Bye-bye.
Bye.
Bye.